I would like to make an added point that comes home to me very clearly. Having been involved in some 44 aircraft development programs and 20 in the Skunk Works, I've seen time and again where the United States industry, the aircraft industry, or any other you want to choose, has demonstrated that when it knows what it is going to produce, it can't be beat. The Lockheed Martin Corporation of today can trace its history back to 1912, when the brothers Allan H. and Malcolm Lougheed established the Alco Hydro Aeroplane Company in San Francisco, California. In 1916, Allan and Malcolm moved their enterprise to Santa Barbara, California, and renamed it the Lockheed Aircraft Manufacturing Company. The firm went on to produce a few aircraft, namely the Model F-1 flying boat and the Model S-1 sport plane. The latter was of the advanced monocoque design that, due to its prohibitive price tag, couldn't compete. Thus, without any airplane orders, Lockheed Aircraft was forced out of business in 1921. In 1926, Allan Lockheed, John Knutson Jack Northrop, and Kenneth Ken J. teamed up and formed the Lockheed Aircraft Company in Hollywood, California. The spelling of Lockheed was changed to Lockheed to prevent mispronunciation. Northrop had joined Lockheed Aircraft in 1920 as a draftsman, and it was he who had designed the S-1 sport plane. This new company used the advanced monocoque design features of the S-1 to create the Lockheed Vega. The company relocated to Burbank, California in March 1928, and by year's end it reported sales exceeding $1 million. From 1926 to 1928, the company produced more than 80 aircraft and employed more than 300 workers who, by April 1929, were building 5 aircraft per week. In July 1929, majority shareholder Fred E. Keeler sold 80% of the Lockheed Aircraft Company to the Detroit Aircraft Corporation. In August 1929, Allan Lockheed resigned. The Great Depression ruined the aircraft market, and Detroit Aircraft went bankrupt. A group of investors headed by Walter Varney and the brothers Robert Ellsworth, Bob Gross, and Cortlandt Sherrington Court Gross bought the company out of receivership in 1932. The syndicate bought the company for $40,000. Ironically, Allan Lockheed had planned to bid for his own company but had raised only $50,000, which he felt was too small a sum for a serious bid. He should have bid, for he would have won back his company. In 1934, Bob Gross was named chairman of the new company, the Lockheed Corporation, which was headquartered at the municipal airport in Burbank. Court Gross was named co-founder and executive. The first successful aircraft that was built in any number, 141 aircraft, was the Lockheed Vega of 1927, which is best known for its several first and record-setting flights by, among others, Amelia Earhart, Wiley Post, and George Hubert Wilkins.
Allan became a real estate agent after he had sold the company, and I actually bought a house from him. But the team that came in, headed by Robert Gross, contained Hall Hibbert, who was the vice president of engineering in those days, Cyril Chapelet, who was his finance and administration man, and that team had many others, of course. I shouldn't say many. There were maybe all of 10 or 15. And they involved one man that came with the company, Carl Squire, who was the marketing manager, if you will. We didn't call him that in those days, but he was the salesman. And the team put together quite a lot of different ideas to carry the company from its wooden airplane legend, if you will, and the production for that matter, into the all-metal world, which they could see coming.
The result was the Electra, an aircraft that was to change the fortunes of Lockheed.
I think this was a pretty courageous move. It was a twin-engine airplane. Lockheed had never built a twin-engine airplane. It was all metal. Lockheed had never built a metal airplane. They had a retractable landing gear. They'd done that once, but this was a little different. And it had two tails on it, which, of course, was the beginning signature, if you will, of one of the designers on the place, Kelly Johnson. And that's when I really first got to know something about Lockheed. Kelly Johnson was Hall Hibbard's sort of chief of advanced design, and he had come from the University of Michigan. And in those days, we had no wind tunnels in the industry, or at least none that I know of. And Kelly used the University of Michigan as a wind tunnel. We had a small tunnel in the basement of the engineering building in Michigan, and I was a student assistant at the time. And so I worked on the Electra and the wind tunnel as a student in Michigan. And that's where the two tails were born. It was a good idea, and still is a good idea for a multi-engine airplane, or a bimotor anyway. In any case, I was interested in it. I met Kelly when he came back to the wind tunnel, and so I came to work for Lockheed after I graduated. Well, that twin-engine Electra was quite a risk for the company. The company had been bought for $40-some-odd thousand, and the development time for this airplane was certainly well over a year or so, which is pretty short. And it was a very successful airplane. It fit a niche in the market and continued to fill a niche in the market, and was actually the foundation of the company.
In the 1930s, Lockheed spent $139,400 to develop its Model 10 Electra, a small twin-engine transport airplane. Surprisingly, a somewhat precocious stalker understudy, Clarence L. Kelly Johnson, then doing postgraduate work in aeronautical engineering, who had participated in the generation of the aircraft's tunnel test data, contrarily had concluded its longitudinal and directional control problems were, as he put it, bad at best. In a somewhat remarkable chain of events, Johnson, during 1933, a year prior to the initiation of the Model 10 tunnel tests, had applied to Lockheed for an engineering job. Johnson took von Hayek at his word shortly after the conclusion of Stalker's Model 10 tunnel study. He returned to Lockheed's Burbank, California offices, master's degree in hand, and again asked for employment. Cyril Chapelet, one of the major shareholders in the new company, and Hibbard were the people who actually hired Johnson as Lockheed's 36th employee. It would be looked back upon as perhaps the single most important personnel transaction in the aircraft manufacturer's history. Kelly's debut, shortly after his arrival, was anything but auspicious. In a meeting with Chapelet and Hibbard during the course of one of his first days at work, he told the engineering group their new Model 10 was only marginally stable. Bluntly, he told the group he did not agree with Professor Stalker's conclusions. He felt a better and safer aircraft could be designed. These comments came as somewhat of a shock to Hibbard. A day after listening to Johnson's matter-of-fact declaration, he cornered the neophyte engineer and orally reviewed his academic credentials in a face-to-face confrontation. He felt certain he could repudiate the Model 10 disparities that had been brought to light. Hibbard would recall years later he came close to firing Johnson on the spot. Several months after the encounter, and after concluding Johnson's claims might have some merit, he told the young engineer to return to Michigan and solve the Model 10's stability shortcomings. Some 73 tunnel runs followed, this number being necessary to narrow the sources of difficulty. The idea of attaching controllable plates to the horizontal tail tips surfaced while run number 72 was underway. These auxiliary surfaces, tested during run number 73, worked very well, particularly after the destabilizing wing root fillets were removed. The next step improved control even further. Full twin vertical tail surfaces now replaced the plates, supplementing the original fuselage-mounted vertical tail. Superb directional control resulted. It was concluded later the original vertical tail was unnecessary, and it was removed. Johnson, who until the Model 10 assignment had been working as a tool designer at Lockheed, returned from Michigan somewhat a hero, and most importantly, a full-fledged member of the engineering staff. In solving the Model 10's problems, he had set the company and its product line on the path to financial success. The company sold 40 in the first year of production. The Model 10 would give birth to several perturbations, including the Model 12 Electra Jr. and the highly successful Model 14 Super Electra. Consequently, Johnson would be partially responsible for the financial latitude implied in the prototyping of the Model 22, which later would become world-renowned as the P-38 Lightning. The cutting-edge Lightning was a twin-edge, twin-boom, twin-tail interceptor pursuit aircraft that eventually became a pivotal combat aircraft in World War II. The design and engineering that went into the P-38 were the handiwork of aeronautical engineers Hibbard and Johnson, and the first example, the one-off XP-38, made its first flight on January 27, 1939. Secretly, a number of advanced features were being incorporated into the new fighter, including a significant structural revolution in which the aluminum skin of the aircraft was joggled, fitted, and flush riveted, a design innovation not called for in the Army specification, but one that would yield less aerodynamic drag and give greater strength with lower mass. As a result, the XP-38 was the first 400-mile-per-hour fighter in the world. It was flown by a USAAC AMC engineering test pilot, First Lieutenant Benjamin Scoville Ben Kelsey, who was a fighter project officer in the engineering division of the AMC and one of P-38's biggest supporters. In fact, he helped convince the USAAC to procure the type. In addition to the P-38 Lightning program, Lockheed Aircraft and its Vega Aircraft Corporation subsidiary, formerly the Air Rover Company, were busy building advanced trainers under license for North American aviation. The Vega, Electra, and Super Electra airliners, and the Hudson, Ventura, and Harpoon bombers and patrol bombers. In 1939, Howard R. Hughes, Jr., billionaire and major stockholder in Trans World Airlines, TWA, put forth an industry-wide request for a 40-passenger transcontinental airliner with a range of 3,500 miles. The earlier Lockheed L-044 Excalibur design didn't fit the requirements, but lent itself to modification into what became the Lockheed L-049 Constellation. But like so many other aircraft manufacturers of that era, it was constantly looking for new business to survive and to keep its relatively small workforce intact. On order for fiscal year 1940 were 65 P-38 Lightnings and a single Lightning derivative designated XP-49. These aircraft, ordered by the then USAAC, were a mere handful to produce, and additional orders were highly sought after. The year 1941 proved much more lucrative due to the expanding wars in Europe and the Pacific. In 1941, military orders increased dramatically for Lockheed. After December 8, 1941, the date America declared war on Germany and Japan, the floodgates opened, and combat and military transport aircraft soon began to stream off the Lockheed and Vega production lines. Between July 1, 1940, and August 31, 1945, the company produced no less than 19,077 aircraft for the war effort. This figure represented 6.6% of all U.S. production during that period and some 9% of the airframe weight total. By the end of World War II, Lockheed was the fifth largest manufacturer of aircraft in the U.S. The war catapulted Lockheed into the upper echelons of financially successful aircraft production companies. Accordingly, it was unable to indulge research and development initiatives that otherwise would have been all but impossible during more austere times. Most notably, as early as 1939, Hal Hibbard and Kelly Johnson had become somewhat infatuated with jet propulsion theory. The power plant concept, already being exploited with considerable efficacy on the other side of the Atlantic, had been placed on the back burner in the U.S. primarily because of the exigencies of the war. By 1944, however, this was no longer the case. Money was made available for studies and hardware development. Working with Hibbard and Johnson were Phil Coleman, Willis Hawkins, and Gene Frost on airframe development, and the far-sighted Nathan Price on propulsion. World War II ended in Europe on May 8, 1945, though the war in the Pacific raged on for another 4+ months. In the interim, the fledgling Skunk Works was busy trying to improve upon its P-80 series of aircraft while it delved into new designs. It was a time of discord because the U.S. War Department planned to cut back on its numerous high-volume aircraft orders. Wartime aircraft production was about to come to a screeching halt. In any event, inside Kelly's lair, the design, development, and engineering on various aircraft projects were constant. And since he was chief research engineer, Johnson was responsible for all of its wants and needs. With the military market dwindling, it came time for Lockheed to reinvestigate the civilian aircraft market. Its large and elegant Constellation would soon ply the skies throughout the world, but there was a need for smaller, feeder-type airliners to shuttle passengers between major cities. During this particular time period, the still rather fledgling Skunk Works entered into unprecedented territory with the creation of several interesting aircraft projects. Its aerodynamic, aeronautical, electrical, fuel, hydraulic, propulsive, and thermal engineering staff was rampant with genius minds, and they came up with many successful offerings. This team, a precursor to the soon-to-be-born Skunk Works, over a period of 6 months, generated a variety of design studies that eventually resulted in the definitive L-133 jet-propelled, canard-configured fighter. Of all-steel construction with an estimated maximum speed of 600 miles per hour, it was to be powered by 2 Lockheed-designed and built L-1000 XJ-37 axial flow turbojets of 5,500 pounds thrust each. As it was, the L-133 and the L-1000 experience, though seemingly non-productive at the time, eventually would bear Lockheed significant fruit. Both concepts were extremely advanced for the early 1940s, even in the light of parallel German and English efforts, and the axial flow engine in particular would prove prescient from a technology standpoint. More importantly, the small but significant experience base resulting from the Maverick airframe and engine would hold the company in good stead when the Air Force finally realized a legitimate need for a jet-propelled fighter. Jet engine technology in the form of propulsion for aircraft had gone through a relatively long and laborious gestation by the time it was successfully applied to Germany's Heinkel HE-178, the world's first successful jet-powered aircraft. Ernst Heinkel's company had initiated jet propulsion studies as early as 1936 under the aegis of a neophyte engineer by the name of Hans von Ohain. Young and brilliant, von Ohain had been invited to join the Heinkel team and to indulge the theories of jet propulsion that had surfaced while he pursued an engineering diploma at the University of Göttingen. Concurrent with von Ohain's work, and in fact preceding it, was a similar effort undertaken by another young and brilliant engineer, Flight Lieutenant Frank Whittle of Great Britain. Though other British countrymen had begun exploring the attributes of jet propulsion during the same 1920s time period, it was Whittle who first concluded that gas turbine and its pure jet thrust were a practical means of aircraft propulsion. Whittle's January 1930 patent predated all other practical attempts to develop a jet engine, and thus later gave credence to his inventor of claims. In the meantime, von Ohain's work, actively funded by the Nazis, had met with considerable success. His first demonstration engine, the HE-S1, had run for the first time during March of 1937. Around it, the Heinkel Company designed the simple high-wing HE-178 testbed aircraft. Following its first flight in the capable hands of Heinkel test pilot Erich Warsitz at the company airfield at Marienhof on August 27, 1939, the HE-178 was used not only to study the jet engine as an aircraft propulsion unit, but also to convince Nazi and Luftwaffe leaders of the jet engine's viability. Its success in the propaganda department later was manifested in the extraordinarily rapid development of such superb operational combat aircraft as the Messerschmitt Me-262 and the Arado R-234, and in turn in the attempted development of a plethora of jet-powered combat types that included the highly advanced Messerschmitt P-1101, Henschel HS-132, the Junkers Ju-287, and the Henkel HE-162. Only the cessation of hostilities prevented German development of a stable of combat jets that could have drastically changed the outcome of the war. On the other side of the Atlantic, U.S. work on jet-powered aircraft had been slow to develop. The reasons were manifold, but in essence they all boiled down to unstoppable momentum in the form of an industrial complex committed to more conventional aircraft forms. On July 25, 1944, Flight Lieutenant A.E. Wall and Pilot Officer A.S. Laban, while flying an unarmed reconnaissance variant of the agile de Havilland Mosquito over Munich, Germany, noticed an approaching enemy aircraft approximately 400 yards astern and closing fast. 5 times, Wall turned into the attacking Me-262, but was unable to gain an advantage. It was only by diving into cloud cover that the Royal Air Force aircraft and its crew were able to escape the frustrating battle. When Wall and Laban returned to their home base at Fermo, near Ancona, Italy, they spent little time equivocating over the capabilities of the long-rumored German jet. They were convinced its performance capability was something the Allies could not easily or safely ignore. So little was known about these advanced machines and their performance envelopes, intelligence personnel were hard-pressed to provide Allied combat crews even minimal information. In turn, available information pertaining to jet engine technology was reviewed with renewed interest, including indigenous U.S. research that had been undertaken during the preceding 2 decades. By 1939, enough progress had been realized to convince the British Air Ministry that research funding was appropriate. Accordingly, a contract was led for a prototype engine, the 855 pounds thrust W-1, to power a proposed jet-powered research aircraft to be built by Gloucester under contract SB 3229, dated February 3, 1940, and designated E-28-39. During March of 1941, following receipt of a perceptive letter dated February 25th from General H. Hap Arnold, then Deputy Chief of Staff for Air, Vannevar Bush formed a special committee on jet propulsion under the chairmanship of Will Durant, ex-chairman of the NACA and a noted proponent of turbo supercharging. During April of 1941, while meeting with British ministry commanders in England, General Arnold was given the opportunity to see the Gloucester E-2839 testbed aircraft while it was undertaking high-speed taxi tests and short hops into the air at the Hucklecote airfield and review in detail the Whittle jet engine. The display impressed General Arnold. He immediately requested that information pertaining to the aircraft and its unique propulsion system be provided his technical staff in London for detailed review. Concurrently, he advised the U.S. State Department of British jet engine developments and requested it assist in the establishment of diplomatic intercourse that would permit the acquisition and dissemination of jet engine information and technology in the U.S. By early September of 1941, the receipt of British jet engine technology, insights, drawings, and hardware via the technical team assembled under command of General Arnold had resulted in a decision to build a copy of the Whittle jet engine. Almost by default, General Electric was the unanimous choice to build the engine, and Bell Aircraft Corporation, also by default, was picked to build the airframe. The British government agreed to provide rights to the U.S. government and also to provide a single complete engine and one of the two E-2839s. Bell, after submitting and getting approval for its aircraft design, received a contract on September 30th, 1941, for 3 Model 27 aircraft with the military designation XP-59A. Beginning on February 5th and ending on February 18, 1944, 3 of the YP-59As were used to evaluate the type as an air combat platform, being flown against a Republic P-47D Thunderbolt and a Lockheed P-38J Lightning. Unfortunately for the first 3-generation jets, their performance against their considerably older, reciprocating engine-powered stablemates was abysmally poor. In mock air combat, the P-47 and P-38 proved faster in level flight, capable of higher maximum altitudes, faster in a dive, and with a higher rate of climb. In only one part of the envelope did the P-59s prove only marginally superior, and that was in turn radius. Some 3 weeks after the Muroc evaluations, General Arnold made it official the P-59A would not become the Air Force's first full-production jet fighter. Its poor performance, when pitted against contemporary U.S. combat aircraft, did not justify operational deployment. More importantly, intelligence data describing the rapidly evolving German jet aircraft initiative was giving every indication a fleet of fighters with performance capabilities far in excess of those being realized by the Bell P-59 was hurriedly being created. What General Arnold also knew, but few others had been privileged to know, was that Lockheed, some 8 months earlier, had been given the go-ahead on a new jet fighter, unquestionably capable of meeting the Luftwaffe threat head-on. While word of the P-59's demise began to spread, the new Lockheed Fighters Flight Test Program was secretly gathering momentum at Muroc. On May 17, 1943, Hibbert and Price were briefed on the status of jet propulsion development and were invited to submit a fighter proposal around Major Frank Halford's de Havilland H-1B Goblin centrifugal flow turbojet engine. 2 months later, Hibbert and Price were queried during the May 17th meeting as to whether Lockheed might consider designing and building a jet fighter around the British power plant. Due in part to the interest shown in jet propulsion by Hibbert, Johnson, and Price, with their L-133, L-1000 studies during the preceding 3 years and their associated attempts to sell both to the Air Force, it was a foregone conclusion that Lockheed's response would be favorable, and it was. At Lockheed, the new L-140 project started in the middle of an incredibly intense production program that was geared to meet the massive generic needs of burgeoning world war, received only minimal corporate attention. Robert Gross, then company president, and Hal Hibbard, chief engineer, assigned the project to Johnson because of his strong interest in jet propulsion, his established organizational skills, and because he was the most competent of the many young engineers on the company's expansive staff. Johnson, in his autobiography, noted the Skunk Works beginning as follows. For some time I'd been pestering Gross and Hibbard to let me set up an experimental department where the designers and shop artisans could work together closely in the development of airplanes without the delays and complications of intermediate departments to handle administration, purchasing, and all the other support functions. I wanted a direct relationship between design engineer and mechanic and manufacturing. I decided to handle this new project just that way. Putting extraordinary pressure on Johnson and his L-140 XP-80 team at Lockheed was the Air Force requirement the aircraft be completed in 180 days or less. On the 16th, it was noted that Mr. Hibbard came in later to make sure the progress pictures were not faked, and the next day, the entire XP-80 team was told that they could all attend the first flight of the aircraft if they could get it done in 140 days. While the team waited for the new engine, miscellaneous checks were run on the airframe, and work continued on minor sub-assemblies and pre-design for the second and third aircraft, which now were beginning to take shape around a new General Electric engine called the I-40. These improved aircraft, officially referred to by Lockheed as L-141s and by the Air Force as XP-80As, as their design evolved, began to differ markedly from their predecessor. The first prototype, 44-83020, was nicknamed Lulu Bell, also known as the Green Hornet, because of its paint scheme. Powered by the replacement Halford H-1 taken from the prototype de Havilland Vampire jet fighter, it first flew on January 8, 1944, with Lockheed test pilot Milo Burcham at the controls. Following this flight, Johnson said, "It was a magnificent demonstration. Our plane was a success, such a complete success that it had overcome the temporary advantage the Germans had gained from years of preliminary development on jet planes." The donated British jet engine and program data had no doubt proved invaluable. In test flights, the XP-80 eventually reached a top speed of 502 miles per hour. At 20,480 feet, making it the first turbojet-powered USAAF aircraft to exceed 500 miles per hour in level flight, following the August 1944 record flight of 504 miles per hour, 811 kilometers per hour, 438 knots, by a special, high-speed variant of the Republic P-47 Thunderbolt. Contemporary pilots, while transitioning to pioneering jets like the Shooting Star, were unused to flying at high speed without a loud reciprocating engine and had to learn to rely on the airspeed indicator. By January 15th, Burcham had conducted 5 flights on the XP-80 for a total of 1.67 hours of flight time. The primary objective of these flights was to obtain preliminary impressions of the XP-80's flying characteristics, as well as information regarding its climb and level flight performance capabilities. A significant amount of flight time also was devoted to evaluating the aircraft's stall characteristics and high-speed performance. The second prototype, designated XP-80A, was designed for the larger General Electric I-40 engine. 2 aircraft were built. 44-83021 was nicknamed the Gray Ghost after its pearl gray paint scheme, while 83022, left unpainted for comparison of flight characteristics, became known as the Silver Ghost. The XP-80A's first test flight was unimpressive, but most of the problems with the design were soon addressed and corrected in the test program. Initial opinions of the XP-80A were not positive, with Lockheed Chief Engineering Test Pilot Milo Burcham commenting that an aircraft he very much enjoyed had now become a dog. The P-80 testing program proved very dangerous. Burcham was killed on October 20th, 1944, while flying the third YP-80A 44-83025. The Grey Ghost was lost on a test flight on March 20th, 1945, although pilot Tony LeVere escaped. Newly promoted to Chief Engineering Test Pilot to replace Burcham, LeVere bailed out when one of the engine's turbine blades broke, causing structural failure in the aircraft's tail. LeVere landed hard and broke his back, but returned to the test program after 6 months of recovery. Sadly, on August 6, 1945, Major Richard Bong, a Medal of Honor winner and the highest-scoring U.S. ace of World War II, was killed in a P-80A while attempting to take off to the south from the Van Nuys, California airport, also apparently as a result of fuel pump failure. After Bong's death, both the USAAF and Lockheed wanted to prove the reliability of the airplane. Thacker tapped Chuck Yeager, plus 2 other pilots, and they put 500 hours on each airplane without further incident. After the war, the USAAF compared the P-80 and ME-262, concluding, despite a difference in gross weight of nearly 2,000 pounds, 900 kilograms, the ME-262 was superior to the P-80 in acceleration, speed, and approximately the same in climb performance. The ME-262 apparently has a higher critical Mach number from a drag standpoint than any current Army Air Force fighter. At least one other important P-80 project became the Skunk Works' responsibility before the rapidly diminishing team moved on to other things. On November 11, 1945, a Gloster Meteor Mk4 of the Royal Air Force set a new world speed record of 606.25 miles per hour. One of the first records of its type to be set by a jet-propelled aircraft, gave rise to an Air Force interest in breaking the record using a slightly modified P-80A. Following a study of the P-80 aircraft by Johnson and various Lockheed and Wright Field engineers, it was concluded a stock P-80A with minimal modification could attain a speed of 615 miles per hour at the required 100-meter maximum sea level altitude. During the course of Chillstrom's numerous passes through the Muroc speed trap, it became apparent that breaking the British record would not be easy. Complicating things was yet another British speed record set by Captain E. M. Donaldson in a Gloster Meteor F-4. And the P-80A was not the only U.S. aircraft in the running. Republic's new XP-84, a similarly straight-wing first-generation jet fighter, was proving its mettle at Muroc by running speed trap at speeds in excess of 600 miles an hour, and thus becoming officially the fastest U.S. aircraft. This left Lockheed's Skunk Works modified P-80, now referred to as the XP-80R, as the only U.S. record hope. Some 9 months after the failed October record attempt, the XP-80R was back at Muroc with Colonel Boyd in the cockpit. On June 18, 1947, everything including the weather was at last in place for the ultimate attempt. Guided by reddish smoke flares set off at each end of the course, Boyd passed through the traps 4 different times per the FAI requirement. Speeds of 617.1, 614.7, 632.5, and 630.8 miles per hour were officially logged, giving an average speed of 623.8 miles per hour, and giving the U.S. its first official world speed record in almost a quarter century. The P-80, formerly named Shooting Star by company executives Robert Gross and Hal Hibbert, would go on to have a long and successful career, not only in the U.S. military, but in the air forces of Brazil, Chile, Colombia, Ecuador, Uruguay, and Peru as well. It would lay claim to the first jet versus jet air combat victory in history and amass an extraordinary record as a fighter, fighter-bomber, and reconnaissance platform during the course of the Korean War. Afterwards, though outdated, it performed yeoman's duty with various Air Guard and Air Reserve units, being finally phased out of U.S. service during 1958. In total, including prototypes and production aircraft, some 1,732 P-80s were built. As just one of their several significant legacies, the XP-80 and the two XP-80As left behind the consummated reality of one of Kelly Johnson's long-held dreams, an experimental department where the designers and shop artisans could work together closely in development of airplanes without the delays and complications of intermediate departments to handle administration, purchasing, and all other support functions. He aspired strongly to have a direct relationship between the design engineer, the mechanic, and manufacturing, and he wanted a chance to prove it would work. The P-80 project provided that opportunity and served as the seed for what would grow into the world's most famous and mysterious aircraft manufacturing institution. In any retrospective describing the history of the Skunk Works, it is necessary to confront the period from 1945 to 1954 with some trepidation. By late 1945, the Skunk Works, as it then existed, had served its purpose and effectively had ceased to exist as a separate entity within the corporate umbrella of the Lockheed Aircraft Company. Regardless, Kelly Johnson had not let the success of the XP-80 program be absorbed by the ever-threatening corporate bureaucracy. Having seen the attributes of the unencumbered design and manufacturing system he and his Skunk Works teammates had created, he was determined to retain its operating philosophy for future endeavors. By the time the P-80 was handed off to Lockheed's Department 28-10 for expansion into a production program, several other aircraft had been brought on board under the Skunk Works operating philosophy for future execution. These projects, the prototypes for the Model 75 Saturn, the XR-60-1 Constitution, the T-33 and T-2V-1 Sea Star, the F-94 Starfire, the XF-90, the RB-69, the X-7, the R-7V2 YC-121F Constellation, the XFV-1, and the YC-130 Hercules would not all be brought to life at once under the Skunk Works umbrella, but rather would arrive with surprising regularity over a period of some 9 years. This steady workflow kept the Skunk Works alive philosophically, but did little to retain any coherent core group that could accurately refer to itself as the Skunk Works. Significantly, during this period, none of these aircraft would be created in a true Skunk Works atmosphere, but rather would utilize various aspects of the Skunk Works approach to prototyping. In every instance, some aspect of design, engineering, or construction was handled by what now is looked back upon simply as the vestiges of the old XP-80 approach. In many cases, the engineering talent was the same as that utilized for the XP-80. Only now it was operating under the aegis of Lockheed California Company, rather than independently under the aegis of the Skunk Works. Keeping it all alive was Kelly Johnson, who was, at times, the only physical manifestation of what remained of the original Skunk Works. Often working on several projects at once, he rarely distinguished between Lockheed aircraft being done in the Skunk Works and aircraft that were not. It was truly a unique period, and one that will forever remain a gray area in the advanced development project's history. Ben Rich, retired LADC president, today refers to it as the time of the Skunk Works Fast Action Shop. Its singular purpose was to create or assist in the development of prototypes quickly and quietly, and with minimal outside help or interference. Then we had our Saturn, a small transport airplane on which we made the most complete market survey we've made on anything up until recently, and it was to be a low-cost per airplane mile airplane. It was good, but it was a complete failure, because it faced 10,000 C-47s that were available at half the cost, and were better in terms of several other regards, larger mainly, and available quickly. Tony LeVere piloted the first flight on June 17, 1946. By late 1947, the handwriting was on the wall. The Saturn was not going to be a successful venture, and there was no reason for Lockheed to throw any more money into its development. In spite of its relatively low operating costs and its better maintenance characteristics, it could not compete against $25,000 Douglas C-47s and similarly cheap C-54s. Flyaway costs of the Saturn were now expected to be between $100,000 and $130,000. Taking advantage of tax write-off options, the two prototypes were released to reclamation crews to be chopped up as scrap. The Constitution was a Navy project, actually started out as a program for Pan American Airlines at 184,000 pounds gross weight. In this project, we used the Skunk Works engineering methods, but we used conventional shop practices. The aircraft was good, but we never got the 5,500 horsepower turboprop engines it was designed for. It ended up one of the world's most underpowered airplanes. The Lockheed R-6V Constitution was a large propeller-driven double-decker transport aircraft developed in the 1940s by Lockheed as a long-range, high-capacity transport and airliner for the U.S. Navy and Pan American Airways. Only two of the aircraft were ever built, both prototypes. Although these two planes went into service with the Navy, the Constitution design ultimately proved underpowered and too large for practical airline use at the time. Other studies using various Wright, Allison, and Pratt & Whitney engines also were offered, but to no avail. Finally, a turboprop version powered by British-built Armstrong Siddeley Pythons was studied, but eventually rejected, as Lockheed Vice President Cyril Chapelet later would lament, "Even if we could have hung bigger engines on it, the Model 89 faced a dim future in the commercial market. Pan American, though seriously interested at first, reappraised its operations at the end of the war, and decided the airplane was too big for immediate traffic needs. Although the Martin JRM Mars flying boat had a slightly longer wingspan, the Constitution remains the largest fixed-wing aircraft type ever operated by the U.S. Navy." From that came the T-33 and then a series of derivatives for interceptors. The T-2V was a Navy program, a carrier-based airplane, and we made as many of those as the Navy had engines for. It was a success. The Lockheed T-2V Sea Star, later called the T-1 Sea Star, is a carrier-capable jet trainer for the United States Navy that entered service in May 1957. Developed from the Lockheed T-33, itself derived from the Lockheed P-80 Shooting Star, it was powered by one Allison J-33 engine. Starting in 1949, the U.S. Navy used the Lockheed T-33 for land-based jet aircraft training. The T-33 was a derivative of the Lockheed P-80 F-80 fighter and was first named TO-2, then TV-2, in Navy service. However, the TV-2 was not suitable for operation from aircraft carriers. The persisting need for a carrier-compatible trainer led to a further, more advanced design development of the P-80 T-33 family, which came into being with the Lockheed designation L-245 and USN designation T-2V. Lockheed's demonstrator, L-245, first flew on December 16, 1953, and production deliveries to the U.S. Navy began in 1956. Some 5,691 T-33s of all kinds eventually were manufactured by Lockheed. An additional 656 aircraft were manufactured by Canada Air in Canada, and 210 aircraft were manufactured by Kawasaki in Japan. Additionally, Well over 1,000 Lockheed-manufactured T-33s eventually found their way into the air forces of over 20 countries around the world, many under the aegis of the Mutual Defense Aid Program. In all, the Navy bought 150 T-2V1s, redesignated T-1A on September 18, 1962, before the Lockheed production program ended during 1959. At this time, right after World War II, there was a whole stable of prototype airplanes, starting with the F-87, F-88, F-90, F-91, and a bunch of bombers. We had lots of prototypes then. The Lockheed F-94 Starfire was a first-generation jet-powered all-weather day-night interceptor of the United States Air Force. A twin-seat craft, it was developed from the Lockheed T-33 Shooting Star trainer in the late 1940s. It reached operational service in May 1950, with Air Defense Command replacing the piston-engined North American F-82 Twin Mustang in the all-weather interceptor role. The F-94 was the first operational USAF fighter equipped with an afterburner and first jet-powered all-weather fighter to enter combat during the Korean War in January 1953. Although requiring much time and delaying the F-94C's entry into service by nearly 2 years, the various airframe, system, and power plant modifications and improvements resulted in the Air Force obtaining a potent interceptor. True, the F-94C was not as fast at high altitudes as other all-weather fighters then being procured by the Air Force, but at low altitudes it was the best of the lot. Furthermore, once modifications eliminated engine flameout when all 24 rockets were salvoed, the closed breech installation of its armament rendered the Starfire substantially more accurate than the F-86D and F-89D, which had open-ended rocket installations. In the end, its limited range was the aircraft's major shortcoming. This, however, was not due to a design oversight, being the ultimate development of a relatively small 1943 design. The F-94C did not have the internal volume required for greater fuel capacity. The first 9 production F-94Cs were accepted by the Air Force during fiscal year 1952. The last 225 Starfires were accepted during fiscal year 1954. Eventually, the F-94C went on to have a lengthy and modestly successful Air Force service life. The XF-90 was the only airplane to defeat the atom bomb. Its military requirement concept was poor, and it was 10 years before the engine for which it was designed was available. It didn't come out good. The Lockheed XF-90 was built in response to a United States Air Force requirement for a long-range penetration fighter and bomber escort. The same requirement produced the McDonnell XF-88 Voodoo. Lockheed received a contract for 2 prototype XP-90s, redesignated XF-90 in 1948. 2 prototypes were built, serial number 46-687 and 688. Developmental and political difficulties delayed the first flight until June 3, 1949, with Chief Test Pilot Tony LeVere at the controls. On August 28th, Johnson noted, "Took a trip to Wright Field in Washington again. The picture is extremely confused. I'm sure we could build our prototype 90 ground attack airplane if we wished, but information which we have collected on the Russian airplanes plus the long delay that would now result before getting into production makes the 90 obsolete. I cannot recommend building it to face airplanes 4 and 5 years from now that will have 15 degrees more sweep, half the weight, and 1/3 the range. Couldn't stand that. Have recommended we drop the airplane in a memo to Hall and Bob on September 5th. A final note on September 6th stated, "Dissolved 90 project permanently." On September 11th, 1950, the McDonnell XF-88 was declared the competition winner. In truth, the XF-90 had been marked for failure from birth. With an ill-defined Air Force specification, a weight problem stemming from an attempt to meet a poorly understood mission requirement, and power plants that could not possibly compensate for the excessive structural overkill, the XF-90's operational prospects were virtually non-existent. On the positive side, Lockheed and the various Skunk Works engineers who conceived and built the XF-90 pioneered the use of 75 ST aluminum, some 25% stronger than the commonly used 24 ST aluminum, verified the viability of the unusual horizontal tail, vertical tail structural control system mix, and indirectly participated in the improvement of the jet engine afterburner. Late in the program, when refitted with the afterburning Westinghouse XJ34-WE-15 engines, both prototypes showed improved performance, but not enough to overcome that of their primary competitor, the McDonnell XF-88. Though none of the penetration fighter contenders would enter production on their own merits, the developed XF-88, in the form of the F-101 Voodoo, would eventually have a long and eventful Air Force career. As to how, according to Johnson, the XF-90 defeated the atom bomb, suffice it to say the second aircraft still exists. Used as a test specimen during the 1952 atomic bomb tests at Frenchman's Flat, Nevada, it survived 3 massive blasts with remarkably little damage. Recent interest in recovering it for the museum display has been discouraged, primarily because it remains highly radioactive. The first XF-90 was sent to the NACA's laboratory in Cleveland, Ohio, and there used as an exemplary structural test specimen. Its final disposition is unknown. XF-90 research, development, test, and evaluation costs totaled at $5.1 million. The estimated unit price for the first 170 production F-90s was estimated to be $670,000. Kelly Johnson lamented that price was as much as the early Constellations. X-7 was a ramjet test vehicle. Made a good many of those things. It was designed to fly at speeds up to Mach 4.0 at over 93,000 feet altitude. It tested the engine for the Beaumark. It was an engine test research vehicle. Post-war analysis of available technology and the attempted assimilation of the massive quantity of data accessed as a result of Nazi Germany's capitulation found the U.S. aerospace industry in an envious but extraordinarily complicated position. The sheer mass of data suddenly laid at the feet of U.S. academicians and technocrats during 1946, coupled with the opportunity for research into virtually every facet of the aerospace sciences, at times proved overwhelming. There seemed to be no limits. Though funding was always an issue of significant contention, the post-World War II perspective on military spending for research seemed to be one of blind benevolence. And, as a result, many obscure programs were given what amounted to blank checks. Though not necessarily falling into the latter category, propulsion system projects created to explore virtually every form of jet, rocket, turboprop, reciprocating, and ramjet power surfaced in overwhelming numbers. Strong military support for these myriad undertakings brought many of them to fruition, including a significant number optimized to explore the attributes of power plants for supersonic aircraft. This was particularly significant in light of the fact the first supersonic flight, on October 14, 1947, had yet to take place. The X-7 was called into production by the United States Air Force, requirement for the development of an unmanned ramjet test plane with a top speed of at least Mach 3. The X-7 project was developed under the AMC designator MX-883 and was given in the Lockheed in-house designation L-171. The L-171 was initially designated the PTV-A1 by the USAF, but was later designated the X-7 in 1951. Despite its first launch being a failure, after redevelopment of the original ramjet, following test flights were successful. During the 130 X-7 flights eventually logged, many test items and projects were parasited onto the basic vehicle. A few of these included the modification of one X-7's wing to accommodate no less than 300 thermocouples to record temperature data and the experimental use of H2O2 fuel additives and boron-based high-energy fuel. The latter was tested on 3 different occasions. Though the results were favorable, the logistics of handling the extremely toxic propellant proved formidable. Besides being dangerous to inhale, even in minute quantities, it also was hypergolic. The X-7A1 and X-7A3 series were followed by 5 X-7Bs, intended to test guidance and control systems in the same way the X-7A tested power plants. The X-7B program was terminated just as the flight test program was getting underway. 12 X-7B flights were completed prior to cancellation. A relatively unmodified version of the X-7A3, known as the XQ-5 and given the name Kingfisher, was developed for use as a dedicated high-speed target drone. Somewhat surprisingly, the XQ-5's performance proved significantly higher than that of the surface-to-air weapons it was designed to test, and it is doubtful that any were destroyed by enemy action. This situation eventually affected the XQ-5's operational career as a Bomark and Nike anti-aircraft missile systems target, as it literally performed its way out of a job. Approximately 80 of the 130-plus X-7 XQ-5 flights attempted were successful, either partially or completely. Problems of bewildering variety surfaced during the course of the flight test program, including range safety concerns, ineffective radar control, malfunctioning autopilots, simple human error, and poor design. But the missile's enviable performance envelope eventually became an item of considerable pride for Lockheed's fledgling missiles and space company. Our first Navy program was next, the XFV-1. A tail-sitting airplane for direct takeoff and landing from a small area on any Navy ship. It was supposed to back down onto the deck. We did excellent in terms of cost and weight, but this aircraft was a failure. It was a failure because we had a bad power plant, and we couldn't look back over our shoulder when flying the thing and judge height. We could practice on clouds all day, but this is the only airplane we ever built, which we were afraid to fly ourselves in the final tests. During 1947, the Air Force and Navy initiated feasibility studies calling for the design and development of several different vertical takeoff and landing aircraft types, including fighters. The Navy in particular found VTOL appealing primarily because of the inherent deck space limitations and the associated shortcomings of steam catapult and arresting gear systems utilized on most then extant aircraft carriers. During early 1953, the first XFV-1 was completed at Lockheed's Burbank facility with an interim 5,850 equivalent shaft horsepower XT-40A6 engine in place of the more powerful YT-40A14 scheduled for actual flight tests. Lockheed test pilot Herman Fish Salmon was assigned to the aircraft as chief test pilot on December 23, 1953, during the course of a high-speed taxi test at Edwards Air Force Base. The aircraft inadvertently became airborne for the first time. Salmon landed moments after leaving the ground. A review of the program's progress now indicated a continuous inability to sustain flight operations sufficiently to retain pilot experience as a result of repeated delays for major component breakdowns. Therefore, since the installation of the engine and propeller did not show the high degree of reliability required, the XFV-1 program was terminated. And there was the Navy version, R-7V2, We had poor performance in the Skunk Works there, because we'd tangled with 17-7 stainless steel, which required 1 million parts in very thin gauges that were very difficult to assemble. We had to do them over twice, and this was a failure. It was a failure, even in the experimental phase, because of the high cost. The airplane flew good and all that, but never went into production. On August 18, 1950, the United States Navy signed a contract for 11 military transport versions of the Lockheed L-1049. The aircraft were to have been convertible troop cargo transports, based on the model L-1049B. The R-70-1 would have also featured round portholes in place of the rectangular ones on Air Force C-121C Constellations. The aircraft entered evaluation service in the Navy's oldest test squadron, VX-1, based in Patuxent River, Maryland. In November 1951, an idea came about to build a turbine-powered version of the R-70-1. This new aircraft was designated L-1249A by Lockheed. In 1954, two R-70-1s, then designated R-7V-1, were pulled off the assembly line for conversion into prototypes for the new L-1249A. The landing gear was strengthened along with the fuselage and wings of the aircraft. Extra fuel tanks were also added on the wingtips of the two aircraft, increasing the fuel capacity to 7,360 gallons. The wings were also shortened from 123 feet to 117 feet 7 inches. The new aircraft was designated R-7V2 and first flew on September 1, 1954. The R-7V2 reached 412 miles per hour, making it the fastest transport aircraft in the world at the time. The two R-7V2 aircraft were delivered to the Navy on September 10th the same year. In 1953, the United States Air Force became interested in the L-1249A project. Two R-7V1 aircraft were again taken off the production lines in 1955 and converted to L-1249A standards. These aircraft, designated YC-121F, were identical to the R-7V2s in service with the Navy. The first YC-121F flew on April 5, 1955, and was delivered to the Air Force in July 1955. The aircraft were put into service with the test squadron of the 1700th Air Transport Group of the Military Air Transport Service, based at Kelly Air Force Base, Texas. After undergoing brief testing, the YC-121F was used on regular basis transportation flights. On one occasion, Lockheed test pilot Roy Wimmer managed to reach a top speed of 479 miles per hour in the YC-121F during a 20-degree dive. On January 25, 1957, a new transcontinental record for propeller aircraft was set by YC-121F, which flew from Long Beach to Andrews Air Force Base, Maryland, in 4 hours and 43 minutes. Lockheed proposed an airliner version of the L-1249A designated L-1249B. This would have had the fuselage of the L-1049E and be equipped with extra fuel tanks on the wingtips, as well as 4 5,500 HP Pratt & Whitney PT-2F1 turboprops. In the end, airlines were still in favor of the piston-engine airliners, so no L-1249B was ever constructed. After completion of their respective flight test programs, the 4 turboprop constellations were dismantled and their parts utilized to keep other constellations in flyable condition. Though modestly successful, the turboprop constellation program proved too little, too late. The jet age by the mid-1950s had filtered down to the airline industry, and with the advent of the de Havilland Comet, the Tupolev Tu-104, and the Boeing 707, it was apparent the future lay in pure jet airliners. Turboprops continued as viable engine options for smaller, short-legged commuter aircraft, but their use on transcontinental and intercontinental airliners proved economically unjustifiable. One of the least known of the Skunk Works' many efforts, the RB-69 program was initiated under the aegis of a CIA contract calling for an aircraft to monitor and document electromagnetic emissions and transmissions in denied territories. The project was begun during 1954 with Kelly Johnson overseeing program manager Luther McDonald, who effectively ran it until 1957, when Fred Kavanaugh took over after being pulled from the P-2V program. McDonald, in order to meet the CIA's mission profile, had proposed the use of Lockheed's venerable P-2V Neptune, then the longest-ranged twin-engine aircraft in the world. Under the auspices of a Skunk Works-type engineering and manufacturing environment, 5 new P-2V-7s and 2 older Navy P-2V-7s became RB-69s and were secretly rolled out at Burbank with Air Force markings during 1955. Delivery flights were made to Edwards AFB North Base, where flight testing was accomplished in considerable secrecy. Referred to by the CIA as Project Cherry, or later Wild Cherry, the objective was to build an aircraft that could safely penetrate denied airspace, gather intelligence data, and return, all without being easily detected by defensive systems. U.S. pilots hired by the CIA to fly the RB-69, like their U-2 counterparts to follow, went through a sheep-dipping exercise that effectively erased their real identities and replaced them with backgrounds that were totally fictitious right down to their contrived names. Each aircraft carried a crew of 12, including a pilot, a co-pilot, a flight engineer, a radio operator, and 8 electronic intelligence personnel to operate the various sensor systems. A mix of penetration and border surveillance flights were flown. One of the first objectives was the collection of power grid data. This was acquired by flying over Western Russia's power lines. When the European operation was compromised by a U.S. officer, he reportedly was entrapped by a female KGB agent. The Wiesbaden missions were terminated. Chinese operations then became highest priority. The Chinese operation began during early 1957 and continued for the following 7 years. The Chinese, frustrated by the RB-69's unfettered night penetrations of Chinese airspace, eventually perfected a night illumination system that successfully exposed the aircraft long enough for fighters to make visual identification and attack. These required that large numbers of Ilyushin Tu-28s and Shenyang J-5s be sent aloft to drop flares. These lit the entire night sky, and in so doing exposed the RB-69s and permitted their interception and destruction. The successes thus realized proved instrumental in the 1964 CIA and Taiwanese decision to remove the type from operational service. Then comes the YC-130. The first 2 prototypes were built using partial Skunk Works methods. It was then taken and moved down to Georgia, who took it on and went into production. That is now heading for a total of 1,500 airplanes. I think the concept was good. It demonstrated our ability to hand it off to another production organization who took it and made it work. On February 2, 1951, the Air Force Tactical Air Command issued requests for proposals to the Boeing, Douglas, Fairchild, and Lockheed Aircraft companies, calling for a medium-weight turboprop-powered transport capable of meeting the specifications and performance criteria outlined in any one of 3 general operational requirements it included. The Air Force demanded a quick response to the RFP, and within days of its release, Art Flock had been assigned as Chief Project Engineer with Willis Hawkins as General Supervisor. Hawkins, at the time, was also in charge of Lockheed's preliminary design department. Skunk Works operating procedures would be utilized as appropriate to expedite design and prototype development. Working with Hawkins were Eugene Frost, Eldon Peterman, Dick Pulver, and Flock, all veterans of earlier Skunk Work projects under Johnson's guidance. Assigned the temporary design number L206 and later becoming the Model 82, the new transport rapidly evolved under Flock's direction. As its configuration matured, so grew the preliminary design group's conviction it was creating a logical yet utilitarian aircraft capable not only of achieving but superseding the basic GOR objectives, specified payload range requirements 8 times that of any then extant design. During the course of design development and mock-up construction, inputs from external sources was invited and reviewed. Air Force and transport personnel were brought in from virtually every segment of the industry. Each was asked to critique the new aircraft and recommend changes or improvements. The resulting information was carefully assessed by Flock and his team and, where appropriate, incorporated into the actual aircraft. Additionally, Lockheed representatives associated with the Model 82's development visited facilities that could provide insight into operational requirements and usage. Interestingly, by this stage of the Model 82's development, Johnson had begun to have doubts about its ability to succeed. Unhappy with its rather proletarian aesthetic qualities, he had reached a point where he refused to sign off the paper proposals being submitted to the Air Force, forcing his boss company, Vice President Hal Hibbard, to overrule him. Because of Korean War pressures, the Boeing, Douglas, Fairchild, and Lockheed proposals were quickly evaluated by the Air Force. On July 2nd, 5 months after first receiving the RFP, Lockheed was informed its proposal had been picked for prototyping over those of the competition. On July 11th, contract AF-33 038-30453 was awarded Lockheed, calling for the construction and flight testing of 2 Lockheed Model 82s, formerly designated C-130 by the Air Force. In short order, the company officially named the new transport Hercules, in concert with its tradition of naming aircraft after stars and constellations. Accordingly, on August 23, 1954, with Stanley Belts as pilot, Roy Wimmer as co-pilot, Jack Reel as flight test engineer, and Dick Stanton as flight engineer, it departed the Burbank Airport at 2:45 p.m. on its first flight. Due in part to the fact the basic mission weight of 108,000 pounds had been 5,000 pounds lighter than guaranteed, cruising speed was some 20% higher. Takeoff distances were some 25% lower. Ceiling and initial climb rates were some 35% higher. Landing distances were some 40% shorter. And single-engine outclimb rates were a stunning 55% higher than predicted. Some 37 years after the first flight of the production aircraft, on May 15, 1992, Lockheed delivered the 2000th production Hercules, a C-130H, to the Air Force. This transport, representing one of the most successful aircraft production programs ever, is only the most recent heir to a legacy that now lays claim to a seemingly endless list of accomplishments.
They came up with a requirement for a tactical transport that had some very unique demands, such as a drive-on, drive-off capability on the airplane, which required the whole aft end of an airplane to open up, and numerous other unique requirements. And many people who saw the design, including the renowned Kelly Johnson, commented that it was the ugliest airplane he had ever seen.
Next, the F-104. We consider that the cost and performance of that model excellent, and I guess after some 2,500 of them having been built around the world, we consider the F-104 series a success. The story of the F-104 began during the Korean War. Kelly Johnson visited frontline squadrons in 1952 to determine what characteristics the next generation of U.S. Air Force fighter planes should possess. At that time, the Republic F-84 Thunderjet and North American F-86 Sabre were being outperformed by the Soviet-built Mikoyan-Gurevich MiG-15, particularly at high altitudes. Predictably, the reaction of the pilots was a demand for greater speed, altitude, and rate of climb, even at the expense of maneuverability, armament, range, ease of maintenance, and creature comforts. Johnson returned to Lockheed with the notion of a lightweight, fast-climbing, high-speed, high-altitude, daylight interceptor. The idea was not exactly a new one, but in pursuing it, Johnson was leading Lockheed onto financially risky ground. The concept of the specialized interceptor had been explored from time to time since World War I, and it had usually been discredited. The problem lay in the interceptor's lack of operational flexibility. No one wanted a combat plane that performed one mission well to the exclusion of all other missions. Johnson was convinced, however, that he and his staff could produce such a quantum leap in aircraft performance that the Air Force would have to take notice. If one could describe the airplane that Kelly Johnson and his team designed in 1952, it would be extreme. The Model 83, as the F-104 was originally known, was created for the sole purpose of flying faster and higher than any other fighter in the world. It was, in essence, the smallest fuselage and wings that could be constructed around the most powerful available engine, one pilot, and the minimum necessary fuel and armament. The F-104's maximum airspeed of Mach 2.2 was dictated primarily by shock wave propagation in the air intakes, by the thermal limitations of the aluminum alloy from which the airframe was constructed, and the amount of stress that the canopy attachment points could take. Air pressure could pull it from the cockpit at speeds above Mach 2.2. To handle temperatures generated at higher speeds, the airframe would have had to have been built of titanium, rendering it far too expensive for mass production. The F-104 was the first aircraft to be powered by the then new 14,800-pound thrust General Electric J-79, an engine that was to set a new standard for power-to-weight ratio. The jet engine air intakes on the F-104 were fitted with movable semicircular shock cones designed to adjust the airflow at various speeds. Such devices became commonplace on jet planes in later years, but were unheard of prior to the F-104. The shock cones were considered so secret that the engine air intakes were completely hidden under aluminum fairings when the Starfighter was first exhibited to the public on April 17, 1956. The engine was not the only revolutionary component in the F-104. The plane's principal armament of a single 20mm cannon may have seemed puny, but it was a very special gun. The Starfighter was the first aircraft designed to use the General Electric M61 Vulcan cannon, a 6-barreled, electrically operated Gatling-type gun that could fire an unprecedented 6,000 rounds per minute, a rate of fire that could use up the F-104's complement of 725 rounds in just over 7 seconds. The Air Force was understandably dubious about the effectiveness of a gun fired from an airplane that was flying as fast as a bullet. Its operational requirement therefore stipulated that the F-104's armament should be augmented with yet another new weapon system, the heat-seeking AIM-7 Sidewinder air-to-air missile. A single Sidewinder was mounted on a rail on each wingtip. The Starfighter's T-shaped tail was also unprecedented. The configuration was arrived at after evaluating no less than 285 different designs. By far, the most astonishing feature of the Starfighter was its wings. In an era of swept wings and broad delta wings, Lockheed broke with convention by giving the F-104 tapered wings of low aspect ratio that were remarkably small. Unlike most aircraft designs, the F-104's wing format was chosen solely for efficiency at supersonic speed, without any consideration for lift, maneuverability, or ease of handling at lower speeds. To compensate, the entire leading edges of the wings were designed to pivot downward to increase lift for takeoff and landing. Lift was also augmented by ingenious trailing edge flaps that had high-pressure air vented from the engine blown across their upper surfaces. With a thickness at the wing root of 4.2 inches, a great deal of design ingenuity was necessary to develop aileron and flap actuators small enough to fit inside them. The edges were so sharp that special covers had to be installed over them to prevent ground crewmen from injuring themselves. Another unusual feature of the F-104's wings that was not obvious from the outside was that they were not connected to each other by a continuous main spar, but by a frame encircling the fuselage. There were penalties to be paid for the Starfighter's speed. The tiny thin wings that endowed the F-104 with its high performance also gave it a blistering stall speed of 198 miles per hour. To help stop the Starfighter, Lockheed gave it a powerful drag chute. It also had a tailhook, similar to those found on carrier-based fighters, but an unusual feature on a land-based fighter. Since the wings could accommodate neither fuel tanks nor landing gear, both had to share the limited space available inside the narrow fuselage. As a result, the F-104 was never to be noted for its endurance, even with extra fuel tanks fitted to the wingtips. The F-104's design also gave it a high wing loading, which rendered its maneuverability less than ideal, particularly at subsonic speeds. In the 1950s, however, it was generally believed that high-G subsonic dogfighting would no longer be a decisive factor in future air battles, which would be fought at high altitudes by supersonic fighter planes armed with guided missiles, aircraft such as the Starfighter. That supposition would be rudely contradicted in the coming decades over Vietnam, the Middle East, and the Indian subcontinent. Lockheed test pilot Tony LaViere flew the prototype XF-104 for the first time on March 4, 1954. The airframe was ready before the J-79 engine, so the XF-104 was first flown with a Wright XJ-65W6 engine. Even though the J-65 only produced 10,200 pounds of thrust, 31% less than the J-79, the XF-104 attained a speed of Mach 1.79 on March 25, 1955, becoming the first fighter to exceed 1,000 miles per hour. The XF-104 was eventually succeeded by 17 service test YF-104As with J-79 engines. Kelly Johnson's faith in the Starfighter concept was vindicated when the YF-104A became the first aircraft type to set both speed and altitude records. Major Howard Johnson climbed to an altitude of 91,249 feet on May 7, 1958, and 4 days later, Captain Walter Irwin attained a speed of 1,404.19 miles per hour. The aircraft also demonstrated an incredible climb rate of more than 60,000 feet per minute. The Starfighter's altitude performance was so impressive that Lockheed later built 3 NF-104As equipped with auxiliary rocket engines and reaction jet controls, like those on a spacecraft, for operation at altitudes so high that conventional controls were no longer effective. Apart from everything else, the F-104 was one of the most exciting-looking aircraft in the world in the mid-1950s. The Starfighter combined unparalleled performance with an appearance that was both extraordinarily beautiful and wholly original. The U.S. Air Force ordered 155 production F-104As in 1955, a number that was raised to 722 in 1958. So many problems remain to be ironed out. However, that the first 35 fighters were diverted to the flight test program. In 7 years, 49 of the 153 that were eventually built were lost to accidents, a staggering 32%. 18 pilots were killed during the same period. In addition, operational experience with the F-104A was raising questions about its limited armament, range, maneuverability, and versatility. Lockheed responded to criticism of the F-104A with a more versatile fighter-bomber version. Designated the F-104C, the improved Starfighter's once pristine lines were cluttered up with external hardpoints for up to 4,000 pounds of bombs, missiles, and fuel tanks. F-104Cs were used in Vietnam by the 435th, 436th, and 476th Squadrons of the 479th Tactical Fighter Wing, TFW, from 1965 to 1968, but Vietnam was not really a suitable venue for them. Since there was nothing for them to intercept, there was no opportunity for the Starfighter to be used to its best advantage. The F-104C also demonstrated that it was still as dangerous to its own pilots as the enemy was. The 435th Tactical Fighter Squadron lost 5 Starfighters to enemy action in Vietnam, but lost another 6 in accidents. In 1958, West Germany, whose Luftwaffe had been resurrected 2 years earlier, was in the market for a supersonic multi-role fighter. They wanted an aircraft able to perform air defense, reconnaissance, interdiction, close support, maritime strike, and even nuclear bombing missions. Despite the fact that the Starfighter had been originally designed as a specialized interceptor, Lockheed managed to adapt it to meet all the Germans' requirements as the F-104G. It incorporated a redesigned airframe, a more powerful version of the J-79 engine, a larger tail, an inertial navigation system, improved radar, and 5 hardpoints for external stores. Over the course of the next 2 decades, it became one of the most widely used fighter types in the world. In NATO alone, Starfighters served in the air forces of Canada, Norway, Denmark, West Germany, the Netherlands, Belgium, Italy, Spain, Turkey, and Greece. West Germany, the largest user, acquired more than 600 of them. The F-104G became, for all intents and purposes, the first Eurofighter. In addition, a further 238 F-104Gs were manufactured in Canada by Canada Air as CF-104s. A total of 1,585 F-104Gs and CF-104s were built, including 2 seat conversion trainers. That was more than 5 times the number of Starfighters built for the U.S. Air Force. The last production version of the Starfighter was the F-104S, an all-weather interceptor developed by Italy in 1968. Air Italia produced 205 F-104Ss for the Italian Air Force, plus an additional 40 for the Turkish Air Force. The last F-104S was completed in 1979, a quarter of a century after the flight of the first Starfighter. Lockheed offered one final development of the F-104 in the late 1960s. Called the CL-1200 Lancer, it differed from the Starfighter in having a longer fuselage, carrying more fuel, a larger shoulder-mounted wing, and a conventional low-set tailplane. The Lancer came along too late to gain acceptance and never got beyond the mock-up stage. The F-104 was the product of a period when air combat was expected to be waged at ever higher speeds and altitudes. Whatever faults the aircraft had are directly traceable to the early 1950s philosophy. By the time the Starfighter became operational, that trend had begun to reverse itself. Today, air combat is often carried on just above the ground. Considering the fact that it had originally been intended as a specialized interceptor of high-flying bombers, Lockheed did a remarkably good job of adapting the F-104 into a multi-role Eurofighter. The F-104 deserves a place in the pantheon of American aviation achievements as the first combat aircraft to fly at double the speed of sound. It also deserves recognition for the part it played in NATO's air defense during the Cold War and for its role in resurrecting the European aerospace industry. Kelly Johnson, in summarizing the F-104 in a paper released on June 18, 1957, presciently noted, "It is very difficult to see where added high speed is worthwhile, and it appears that the development of armament, radar, and fire control systems is the most fruitful field to our research efforts over the next 5 years. Above all, it deserves to be remembered as the breathtaking missile with a man in it." The U-2s, we underran our contract on that and gave back the government over 20% of the first contract. It was a success. It was the first time when the Skunk Works went into production. Because of security and other reasons, we, for the first time, made more than 2 of anything, and we made the complete line of the U-2s and the other versions that have come from it. High-altitude strategic reconnaissance philosophy was first articulated during late 1952, when an Air Force major by the name of John Seaberg placed on paper ideas he had for achieving sustained flight at ultra-high altitudes. Seaberg had noted the new generation of turbojet engines could be mated to an aircraft with an extremely efficient high-aspect ratio wing and achieve cruising altitudes far in excess of any aircraft then in service. On May 18, 1954, some 2 weeks after returning from Washington, D.C., a new proposal for a high-altitude cruise aircraft from Lockheed's preliminary design organization arrived on Seaberg's desk for review. Johnson's own insights into the beginning of the aircraft are only thinly recounted in his U-2 log. December 1953. We started an investigation of wing area modifications and stripping procedures to modify the F-104 airplane to get the maximum possible altitude for reconnaissance purposes. Seaberg and his fellow right field engineers spent 3 weeks evaluating the Johnson proposal.
In the early 1950s, the United States had a real requirement to overfly Russia to find out the status of their development of long-range missiles. There was no airplane in the United States or in the world that could safely overfly Russia at that time. Lockheed made an unsolicited proposal to Trevor Gardner, the Undersecretary for Research and Development for the Air Force, on a very specialized airplane. We promised to build within 8 months 20 airplanes for $22 million, including spares, that would do the job required. The program was turned over to the CIA, who then chose Mr. Richard Bissell, an economist, to run the program. Richard Bissell became a very good engineer, and he not only was our director on the U-2 program, but he also followed through with the development of the Mach 3 Blackbird.
When I first met Kelly, I had been working for nearly a year for Allen Dulles. I joined Allen's organization early in 1954. Toward the end of November, I was summoned one afternoon into Allen's office, and I was told, with absolutely no prior warning or knowledge, that one day previously, President Eisenhower had approved a project involving the development of an extremely high-altitude aircraft to be used for surveillance and intelligence collection over denied areas in Europe, Russia, and elsewhere. We had, on the basis of Kelly's proposal, an almost impossible schedule to meet. It was almost impossible for Lockheed, but I can assure you that it was also an extremely tight schedule working within the bureaucracy.
Given the temporary design number CL-282, it consisted of a slightly modified XF-104 fuselage and associated vertical and horizontal tail surfaces. Most noticeable, however, was the deletion of the XF-104's distinctive trapezoidal-shaped wings, and their replacement by a high aspect ratio wing of extraordinary span. Designed into the latter were 4 integral fuel tanks complemented by a 5th tank in the fuselage. Together, these provided a total fuel capacity of 925 gallons. After a thorough but rushed review, Seeberg and his staff rejected the CL-282. Johnson, after receiving word of the negative report, would note, June 7, 1954, received a letter which turned down our proposal on the basis that it was too unusual, that it was a single-engine aircraft, and that they were already committed to the Martin program. When the Air Force informed Johnson of its decision to eliminate the CL-282 from contention, Johnson decided to pursue funding through other channels. Johnson's timing could not have been better. Numerous sources had begun to input data into the U.S. intelligence community indicating the Soviet Union was moving ahead quickly with an extensive family of liquid-fuel, nuclear warhead-equipped intercontinental ballistic missiles. On November 19, 1954, Johnson would make the following log entry. I met with the Government Advisory Board. They wanted to be reassured that our proposal was technically feasible. They believed my story that we could make such an airplane in the time mentioned, and also asked why Lockheed seemed to be the only one who could do this job. General Putt answered graciously that we had proven it 3 times. As it turned out, this was a momentous decision. In one master stroke, Johnson, with Gross's blessing, had transformed the virtually non-existent Skunk Works into not only a full-scale advanced design and engineering team, but a production facility as well. Secrecy had mandated the change. Eisenhower had agreed the funding and direction of the project, to be codenamed Aquatone, would be through the offices of the CIA rather than the Air Force, with Richard Bissell to direct. Earlier on November 9, 1954, Trevor Gardner had visited with Lockheed President Robert Gross and Johnson at Lockheed's Burbank facility. Following a review of the full-scale U-2 mock-up, Gardner gave official confirmation of project approval and a directive to go ahead with prototype construction. Johnson promised the first Aquatone aircraft would be in the air no less than 8 months after the first metal was cut. On December 10th, the design was frozen, and on December 20th, Johnson noted in his log, "Working like mad on airplane. Initial tunnel tests successful." Among the unique weight-related accomplishments of the design program were the following. Wing weight was kept to an almost unbelievable 4 pounds per square foot. The landing gear was a bicycle arrangement with the heaviest component consisting of a single main strut. The tail assembly was attached at the center fuselage by only 3 bolts. The side-opening canopy was manually operated. The control system was unboosted. Hydraulically actuated systems were kept to a minimum. There was no cockpit pressurization, and there was no ejection seat. On the morning of August 4th, 1955, Johnson, Ernie Joyner, Glenn Fulkerson, Bob Murphy, and several other Skunk Works personnel watched as Levier climbed into Article 341 in preparation for its first real flight. Given the call sign Angel 1, the aircraft was to be chased by a company-operated C-47, with Johnson and test pilot Bob Matty as observers. Customers also had been brought in from Washington, D.C., and they arrived at the test location by transport just prior to Levier's takeoff. Levier recalls the first takeoff and climb, taking place at 3:55 p.m., went perfectly, and that he encountered no problems or difficulties during the ascent. Leveling at 8,000 feet, he spent 45 minutes cycling the landing gear, deploying and retracting the flaps, exploring stability and control characteristics, checking engine temperatures and exhaust pressure ratios, and practicing power-off stalls. There were no malfunctions of any kind. LeVere completed a total of 20 flights in the Angel before being transferred back to the F-104 and other Lockheed flight test programs on September 1st. Additionally, LeVere became the first pilot to take the aircraft to 50,000 feet. The latter required the use of a partial pressure suit. This had forced LeVere to go through the Air Force's high-altitude training program. When he completed the curriculum at the age of 42, he was at the time the oldest pilot to do so. During this initial flight test period, the Air Force, at Johnson's recommendation, assigned the innocuous U-2 designator to the aircraft as its formal military alias. The flight test program during the remaining months of 1955 progressed smoothly. December 1st marked the U-2's first-year anniversary, which Johnson duly noted. "We have built 4 flying airplanes, have the 9th airplane in the jig, and have flown over our design altitude any number of times. We've trained crews and are developing the Bakersfield factory. It's been quite a year." On June 19, 1956, CIA pilot Carl Overstreet departed Wiesbaden on the first operational flight. After overflying Warsaw, Poland, and returning via Berlin and Potsdam, he landed without incident and delivered to the U.S. intelligence community the first ever surreptitiously taken U-2 photos. The results were spectacular. The quality of the imagery generated by the Type B folded optics camera was everything the CIA had hoped for. Resolution, contrast, and quality were far beyond anything previously seen. Baker, at Harvard University, and an astronomer by training, was one of the leading lens designers in the U.S. during the 1940s and 1950s. By now, Soviet diplomatic circles were impacted. The U-2 flights had been tracked with little difficulty by Russian radar, and the Soviet government was embarrassed by the ease with which the aircraft were able to penetrate Russian airspace. The military repercussions were great. In a communiqué dated July 10, 1956, the Soviet ambassador to the U.S. in Washington was asked to deliver a formal protest to the U.S. government and request that the overflights cease. In responding, U.S. diplomats denied that any military aircraft had been involved in such activity. This was, of course, true, as the CIA was a civilian and not a military agency. During 1958, the Soviets began to gather momentum in their efforts to develop an effective U-2 countermeasure. The SA-2, an improved surface-to-air missile, eventually codenamed Guideline by the West and equipped with a warhead that had a kill pattern with a diameter of about 400 feet, was pushed into service and for the first time threatened the U-2's high-altitude dominance. Though the estimated 2% probability of kill was low, for the first time the U-2 was forced into taking the new SA-2 launch sites into consideration. By the end of its 3rd year of operation, the U-2's intelligence-gathering ability had become the single most important tool in the entire U.S. intelligence community arsenal. CIA U-2 operations were not confined to the Soviet Union during this period. During late September of 1956, Gary Powers flew across the eastern Mediterranean and gathered intelligence data on the positions of British and French warships as they prepared to aid the forthcoming Israeli invasion of Egypt.
CIA, I had heard of it before this. I knew what its purpose was. I knew what they did, but they were a very little known organization at that time, and I probably knew as much or as little as anyone else. I knew hardly anything about it except that I knew it was a highly secret intelligence gathering organization. They had this plan with a new plane to do espionage over the Soviet Union. I knew that flying this airplane without permission over the Soviet Union was spying. I knew that it was. But I really don't think that in the true sense of the word spy that I ever considered myself a spy. I was a pilot flying an airplane, and it just so happened that where I was flying made what I was doing spying. I felt that it was a very necessary thing, and I was very proud of my country for having, I guess the word is the guts to do this, because I had felt, and a lot of people had felt, that we had not been responding the way that we should have responded to threats from the communist nations such as Korea and so forth. When I found out that they were, I was very proud.
Further flights followed during the Suez Crisis and later, during crises involving Syria, Iraq, Saudi Arabia, Lebanon, and Yemen, all to gather intelligence data on military activities and the eternal warring between these various Middle Eastern countries. Additionally, U-2 overflights over the Xinjiang and Jiangxi provinces in China began on December 6, 1958. On May 1, 1960, the U-2 was thrust into the public spotlight when one flown by Francis Gary Powers was shot down over Sverdlovsk by a surface-to-air missile.
An unarmed plane, a U-2 weather research plane based at Adana, Turkey, piloted by a civilian, has been missing since May 1. During the flight of this plane, the pilot reported difficulty with his oxygen equipment. Mr. Khrushchev has announced that a U.S. plane has been shot down over the USSR on that date. It may be that this was the missing plane. It is entirely possible that having a failure in the oxygen equipment, which could result in the pilot losing consciousness, the plane continued on automatic pilot for a considerable distance and accidentally violated Soviet airspace. The United States is taking this matter up with the Soviet government with particular reference to the fate of the pilot.
Captured, Powers became the center of the resulting U-2 incident, which embarrassed Eisenhower and effectively ended a summit meeting in Paris.
I shall bring up the open skies proposal again at Paris, since it is a means of ending concealment and suspicion. My final point is that we must not be distracted from the real issues of the day by what is an instance or a symptom of the world situation today. This incident has been given a great propaganda exploitation. The emphasis given to a flight of an unarmed, non-military plane can only reflect a fetish of secrecy.
The incident led to an acceleration of spy satellite technology.
I felt that by talking to them as freely as I could, tell them the absolute truth about everything that they knew about, I could establish a basis of truthfulness. So when it did come to sensitive something that I didn't want to tell them about, I could lie and they would believe me, and this worked fairly well. But there was still this threat of torture, and I felt that if I were tortured, that any information they wanted, I might give. I didn't know how I would react to torture, so that if I could prevent this anyway, then I had to do it, because I had some information that they could have used.
Remaining a key strategic asset, U-2 overflights of Cuba in 1962 provided the photographic evidence that precipitated the Cuban Missile Crisis. On October 22, 1962, President Kennedy made his now famous speech revealing publicly that Cuba had acquired an extensive offensive weapons capability, including MRBMs and IRBMs. In an unquestionably threatening tone, Kennedy declared that any Cuban missile launch would be regarded as an attack by the Soviet Union on the U.S. and that massive retaliatory action would result. He also declared a naval quarantine of Cuba until all Soviet offensive weapons were removed from the island.
It shall be the policy of this nation to regard any nuclear missile launched from Cuba against any nation in the Western Hemisphere as an attack by the Soviet Union on the United States, requiring a full retaliatory response upon the Soviet Union.
During the crisis, a U-2 flown by Major Rudolph Anderson Jr. was shot down by Cuban air defenses. On October 26th, communications with the Soviets indicated they would begin dismantling the Cuban missile sites. On October 28th, this was confirmed. The Cuban Missile Crisis, due in no small part to the photographic intelligence provided by the U-2 surveillance program, had come to an end. Frequent Cuban overflights continued. They still were in progress when President Kennedy, remarking, "I must say, gentlemen, that you take excellent pictures." As surface-to-air missile technology improved, efforts were made to improve the aircraft and reduce its radar cross-section. This proved unsuccessful, and work began on a new aircraft for conducting overflights of the Soviet Union. In the early 1960s, engineers also worked to develop aircraft carrier-capable variants, U-2G, to extend its range and flexibility. During the Vietnam War, U-2s were used for high-altitude reconnaissance missions. In 1967, the aircraft was dramatically improved with the introduction of the U-2R. Approximately 40% larger than the original, the U-2R featured under-wing pods and an improved range. The phasing in of the U-2R over Vietnam led to the phasing out of the remaining Air Force U-2Cs. The last of the original U-2Rs was delivered from the Skunk Works Palmdale facility during December of 1968. As Johnson would note in the log, "We are rapidly running out of work on this program." This was joined in 1981 by a tactical reconnaissance version designated TR-1A. The introduction of this model restarted production of the aircraft to meet the U.S. Air Force's needs. The U-2R and TR-1 were critical contributors to Desert Shield and Desert Storm operations. They flew with a variety of sensors for high-resolution photography, radar mapping, and low-light observations. Intelligence agencies, field commanders, the Pentagon, and even the President used this information to identify military targets, estimate enemy troop strengths, and make battle damage assessments. In the early 1990s, the U-2R fleet was upgraded to the U-2S standard, which included improved engines. A production-configured re-engined U-2R completed its qualification phase of flight test at Palmdale during late 1993. 3 U-2Rs incorporating the engine and other upgrades were officially delivered to the Air Force from Palmdale to Beale Air Force Base, California on October 28, 1994. The upgraded aircraft are officially designated U-2S in the single-seat configuration and U-2ST in the two-seat trainer configuration. A total of 37 U-2Rs will be brought up to the new standard by the time the retrofit program ends during 1998. NASA's ER-2s also will be upgraded starting in 1996. Despite its advanced age, the U-2 remains in service due to its ability to perform direct flights to reconnaissance targets on short notice. Though there were efforts to retire the aircraft in 2006, it avoided this fate due to the lack of an aircraft with similar capabilities.
I still think it's one of the best airplanes ever made. It was just a tremendous thrill to be able to look down at the Earth far below, and actually early in the mornings, with the sun just coming up, you could see the curvature of the Earth out on the horizon, and it just beautiful. Early in the program, flying this, it was thrilling to know that you were doing something that no one else had ever done, except just a very few people who flew this particular airplane. Each flight broke an altitude record.
The Jetstar made 2 of them. They were a success as far as the prototypes went. When it was handed over to our Georgia division, here's a case where it wasn't handed over good. It was almost completely redesigned. Went to 4 engines instead of 2. The cost almost killed us in the end, but as far as the prototype part of the program goes, it went well. During the latter part of 1955, it became apparent to the Air Force that its aging and somewhat eclectic utility transport and twin-engine training aircraft fleet was in need of replacement with contemporary hardware. Many of the aircraft then in use for these missions could trace their origins back to the pre-World War II period. All were powered by reciprocating engines. Compounding the Air Force's problem was a post-Korean War funding shortfall that severely restricted new aircraft acquisitions. Nevertheless, the service elected to move ahead with long-term plans under the aegis of the UTX and UCX specifications. In order to do this, it required that the companies submitting proposals also be willing to fund their respective prototypes using their own money. Concurrent with its August 1, 1956 request for proposals, the Air Force made it understood that, if funding constraints were lifted, it would order up to 300 of the winning design. Making the new aircraft doubly enticing for manufacturers was the prospect of corporate and commercial sales beyond those to the military. Kelly Johnson later would note, "With the military as a ready prospect for such a sizable order, we pulled out all the stoppers. We assembled our technical teams, studied the requirements, drew up plans, designed, and built." While the new model CL-329 was conceived, engineered, and flown in less than 8 months, Lockheed had in fact spent some $7 million during the preceding 13 years studying large jet-powered transport aircraft that involved technology advances directly applicable to its forthcoming utility training aircraft. During 1956, the Air Force informed industry there was a military requirement for a small jet transport to meet its UCX and UTX specifications. Johnson and his Skunk Works team, with corporate approval, immediately initiated preliminary design studies based on a small-scale L-193 variant. Accordingly, Johnson decided that in order to get the CL-329 into the air at the earliest possible date, it would be necessary to power it with British-built 4,850-pound thrust Bristol Orpheus 1.5 turbojets. On the morning of Wednesday, September 4, 1957, the first Jetstar taxied out onto the Edwards Air Force Base dry lake bed. At 8:58 a.m., the Jetstar became airborne for the first time. It had met Johnson's September 4th first flight deadline and had beaten by 2 minutes the predicted 9 a.m. departure time. Air Force Phase 2 testing was completed during February of 1958 using the first aircraft. It was determined that the Jetstar had excellent flight and performance characteristics. On June 17, 1958, the first Jetstar embarked on a promotional trip to demonstrate its transcontinental range and high cruising speeds. Unfortunately, though the demonstration tour proved a success, a national recession dictated the Air Force delay its plans to acquire the aircraft for operational services. As a result of the Air Force's intransigence concerning 4 engines versus 2, during January of 1959, Pratt & Whitney J212A turbojets were selected to power the Jetstar in its production configuration. On October 31, 1958, the Jetstar was picked by the Air Force over North American's NA-246 submission to meet the requirements of the UTX specification, which Lockheed had not originally planned to accommodate. During October, the Air Force announced its plan to acquire the Lockheed aircraft under the designation T-40A. Shortly afterwards, however, it withdrew the initial decision and awarded the contract to North American for what became the T-39A Sabreliner. Eventually, 211 trainer and light transport Sabreliners would be acquired by the Air Force and Navy while Lockheed's Jetstar starved for orders. It was not until June of 1960 that an initial Air Force order for 5 Jetstars finally arrived. The first of these, by now referred to as C-140A by the Air Force, was delivered during April of 1961. By January of 1962, Lockheed, having spent $100 million on the Jetstar program, was facing an $80 million loss. This was attributable to the Air Force's initial indications it would buy some 300 aircraft, when in fact, by mid-January of 1962, it had bought only 16. When Jetstar production ended during 1980, With the delivery of the 204th and last aircraft to the Iraqi government, Lockheed had lost a considerable quantity of money, but had learned some very valuable business lessons. The aircraft, regardless of its financial status, proved to be a successful corporate transport. Several versions eventually were built by Lockheed, including the C-140A, the C-140B, and the VC-140B for the military, and the Jetstar 6, the Jetstar 8, and the Jetstar 2 for the corporate market. Then came a number of Mach 3.0 types, the first one of which you'd be familiar would be the YF-12A. Its gross weight is still secret, but the cost performance was excellent. It was a success. Didn't produce any because there wasn't any threat. Not until the backfire bomber showed up. Of the many aircraft whose origins can be traced back to Lockheed's renowned Skunk Works, none is more significant than the A-12. More than any other aircraft, this titanium masterpiece represented the apex of aeronautical engineering in its day, not only at Lockheed, but at every significant aerospace engineering bureau around the world. Today, over 3 decades after its first flight, it remains the aircraft by which all others are judged. Project Suntan had given Kelly Johnson and the Lockheed Advanced Development Team engineers a significant opportunity to explore the attributes of hydrogen propulsion systems. Equally as important, however, Suntan also permitted the exploration of advanced airframes, optimized for the first time to cruise at speeds well in excess of Mach 3. Soon after the U-2's first flight during 1955, Richard Bissell moved quickly to organize the research and development of follow-on systems, including what was to become the A-12. New studies, conducted under the codename Gusto, were initiated exploring the design and possible development of a totally new subsonic reconnaissance platform that would be designed from the start to incorporate the lowest RCS obtainable. The resulting analysis concluded that supersonic speed, coupled with the use of radar-attenuating materials and radar-attenuating design considerations, greatly reduced the chances of radar detection, though it did not reduce it to zero. Lockheed Aircraft Corporation and the Convair Division of General Dynamics during the fall of 1957 were to respond to a general operational requirement calling for a high-speed, high-altitude reconnaissance aircraft, but to do so without a formal contract or government funding. Johnson spent virtually every available minute working on the advanced aircraft program, which he sometimes jokingly referred to as the U-3. Project Gusto now was terminated, and a new codename, Oxcart, was assigned. Ben Rich would note that the A-12 was composed of 85% titanium and 15% composite materials. Learning to work with titanium proved to be a major undertaking. The myriad breakthroughs pioneered by the Skunk Works manufacturing team in conquering this metal remain one of the great and unheralded successes of this most incredible program. Just a great deal of work with the many problems we have trying to get this airplane built. Everywhere you turn, there are tremendous problems requiring invention, new systems, and money. An official first flight with appropriate government representatives on hand now was made on April 30th. Nearly a year behind schedule, the aircraft became airborne for the first time. With Lou Schulk at the controls, the aircraft lifted off at 170 knots. The landing gear was retracted and a climb was made to 30,000 feet. A top speed of 340 knots was reached during the flight, which lasted for 59 minutes. Following an uneventful landing, Schulk expressed satisfaction with the aircraft's stability and the way it handled. On the second flight, on May 4th, the A-12 went supersonic for the first time, reaching Mach 1.1. Problems were minimal, and Johnson began to feel confident that the flight test program would progress rapidly, possibly recovering some of the time that had been lost in the drawn-out manufacturing process. The Cuban Missile Crisis now reinvigorated the program. The loss of Major Rudolf Anderson's U-2 over Cuba on October 27th underscored the increasing vulnerability of this subsonic platform when operating in denied airspace, and this was not lost on intelligence community offices involved with the overflight program. At the end of 1962, two A-12s were in flight test, one powered by J-75s and the other powered by one J-75 and one J-58. A speed of Mach 2.16 and an altitude of 60,000 feet had been achieved. Flight test progress was still slow, and the engine delays and thrust deficiencies remained a major concern. Meanwhile, by the end of 1963, the CIA's A-12 flight test program had resulted in 573 flights, totaling 765 hours. 9 aircraft were on hand at the test location. It should be noted at this point that on July 24, 1964, President Johnson made the first official announcement concerning the forthcoming Lockheed SR-71. With the A-12 situation vacillated back and forth between an operational commitment and continued wait-and-see, flight testing of the YF-12A had continued. During July of 1966, Johnson wrote in the log, "We were directed to give up further flying of the YF-12As, although we had proposed shooting down a drone at Holloman to get the effect of ground clutter for low-altitude targets." The following August 5th, he wrote, "We've laid off half of our test crew on the YF-12A and are maintaining only enough people to store the airplane or send it to Burbank. We are very near the end of this program." As late as January 26, 1967, Johnson made the following comments in the A-12 log. "We jointly agreed there would be just one round and not two. That seems to have been a very accurate evaluation, as it seems that 30 SR-71s give us enough overflight reconnaissance capability, and we don't need the additional 10 A-12 aircraft." On January 5, 1968, an official wire closing down the F-12B was received from the Air Force. The YF-12A program would be formally ended on February 1st. In a final disheartening move, the Air Force, on February 5th, sent Johnson a letter instructing Lockheed to destroy the A-12 F-12 tooling. The final A-12 flight took place on June 21, 1968, when the last remaining aircraft, number 131, was ferried from the test location to Palmdale by CIA pilot Frank Murray and placed in storage. It would remain there for the following 2 decades. On June 24th, Johnson wrote, "While the intelligence community in Washington wanted very much to keep the A-12 program going, the present financial situation cannot stand the strain. It's a bleak end for a program that has been overall as successful as this." In summary, the A-12 program lasted just over 10 years from its inception during 1957 through its termination during 1968. The Skunk Works produced 15 A-12s and 3 YF-12As. 5 A-12s and 2 YF-12As were lost in accidents. 2 pilots were killed, and at least 6 had narrow escapes. In addition, 2 F-101 chase aircraft were lost with the Air Force pilots during the A-12 test program. The main objective of the program, to create a reconnaissance aircraft of unprecedented speed, range, and altitude, was triumphantly achieved. It may well be, however, that the most important aspects of the effort lay in its byproducts, the notable advances in aerodynamics, engine performance, cameras, electronic countermeasures, pilot life support systems, and the arcane art of milling, machining, and shaping titanium. Altogether, it was a pioneering accomplishment, almost certainly never to be repeated in the history of aviation. The YF-12A developed into the SR-71, and in that case, again, the cost performance was excellent as we gave back to the government well over $19 million on the contract, and we consider it to be a success. On December 6, 1962, Kelly Johnson noted in his log, "Working on R-12 Universal Airplane using company work order. Can get no decision on any military version of the aircraft, but there does seem to be considerable interest in it." Johnson's rationale for this design was based on the premise that if he produced a single platform capable of performing the reconnaissance, recon strike, or intercept role depending on customer needs, it would greatly simplify production, and it eliminates the necessity of the Air Force deciding which version they want to buy. 7 days later, the Skunk Works was visited by several SAC personnel, and Johnson logged that they wanted to see what kind of a reconnaissance version would meet SAC's needs. We prepared our proposal for a 140,000-pound reconnaissance airplane capable of carrying 4,300 pounds of reconnaissance gear and gave it to Colonel Templeton with a forwarding letter. By March 18, 1964, R-12 construction was moving along with considerable rapidity, but contract negotiations had yet to be concluded with the Air Force. Johnson noted in the log, "Spent several days on the first 6 R-12s. It is extremely difficult to get a reasonable profit for what we do, and no credit is given for the fact we operate more cheaply than others." All activity relating to the R-12 and RS-12 configurations had, of course, been kept completely under wraps in the Skunk Works and within the confines of the involved Air Force and CIA offices. On July 24, 1964, however, President Johnson made his memorable announcement revealing to the world the existence of Lockheed's Mach 3-capable reconnaissance aircraft. "I would like to announce the successful development of a major new strategic manned aircraft system which will be employed by the Strategic Air Command. This system employs the new SR-71 aircraft and provides a long-range advanced strategic reconnaissance plane for military use, capable of worldwide reconnaissance for military operations. The Joint Chiefs of Staff, when reviewing the RS-70, emphasized the importance of the strategic reconnaissance mission. The aircraft will fly at more than 3 times the speed of sound. It will operate at altitudes in excess of 80,000 feet. It will use the most advanced observation equipment of all kinds in the world. The aircraft will provide the strategic forces of the United States with an outstanding long-range reconnaissance capability." In August 1964, Kelly Johnson phoned Bob Murphy and asked him if he wanted to work on the new reconnaissance aircraft. At the time, Murphy was a superintendent in charge of D-21 drone production. He accepted the offer and was immediately briefed by Johnson, who said, "I want you to go to Palmdale and get Site 2 away from Rockwell. Hire the people you need. The pieces of the aircraft will be up with you on November 1st, and I want her flying before Christmas." The SR-71 was 107 feet, 5 inches long, had a wingspan of 55 feet 7 inches, and a wing area of 1,605 square feet. It stood 18 feet 6 inches high to the top of the rudders, and its gross weight varied from 135,000 pounds to over 140,000 pounds. The effect of thermodynamic heating brought about by the aircraft's extreme operating envelope was a major factor affecting its construction. Fully 93% of the airframe was built from titanium, while the remaining 7% consisted of laminates, of phenylsilane, silicone, asbestos, and fiberglass to help reduce the aircraft's RCS. The SR-71's forward fuselage has a circular cross-section and is of semi-monocoque construction. It housed the pilot and a reconnaissance system operator, RSO, seated in tandem, the front undercarriage, fuel cells, and the air refueling receptacle. The delta wing features 2 prominent engine nacelles, each mounted at mid-semispan and blended into the wing to further reduce RCS. 2 rudders mounted on top of each nacelle and canted inboard 15 degrees from the vertical also reduced the aircraft's radar signature. A large aft-moving spike extends forward from each nacelle, which helped to regulate mass airflow to the two Pratt & Whitney J58 engines. The maximum fuel load weight for the SR-71 was 80,280 pounds, and it was carried in 6 fuel tanks. Built to cruise in afterburner at Mach 3.2 and at altitudes in excess of 80,000 feet, the aircraft encountered extremely high airframe temperatures generated by thermodynamic heating. This, coupled with the diverse operating envelope of its Pratt & Whitney J58 engines, required the development of a special fuel which served not only as the source of propulsive energy, but also as a hydraulic fluid optimized in the engine hydraulic system to activate the main and afterburner fuel nozzles. On the ground, the aircraft was only half filled with fuel, and then pressurized using LN2 to 1.5 psi above ambient pressure. Shortly after takeoff, the SR-71 would rendezvous with a tanker and get topped off. The Air Intel control system was a major innovation used to exponentially increase the speed performance of all Kelly-Johnson's so-called Blackbirds. At Mach 1.4, the outlet doors located in the exterior of the engine nacelle began to modulate automatically in order to obtain a prearranged ratio between dynamic pressure outside the inlet throat and static duct pressure inside the inlet cowl. At 30,000 feet, the inlet spikes unlocked and, at Mach 1.6, began moving rearward, achieving their fully aft position at Mach 3.2, design cruise speed. Cruising covertly during operational missions at speeds in excess of a mile every 2 seconds, it was essential that the SR-71's navigation system was both highly accurate and not reliant upon external navigation aids to ensure the aircraft remained on the black line. At the heart of successful mission accomplishment, therefore, was the Nortronics Astro-Inertial Navigation System, or ANS, designated NAS-142 V2. Originally designed for the Douglas Skybolt air-to-surface ballistic missile, which was canceled in 1963, it proved to be a perfect solution for navigating the SR-71 after a few modifications and updates. The system combined data from the inertial navigation platform with a time datum accurate to within 5 milliseconds. Position updating was achieved automatically by astro-tracking at any one time 6 of the 52 most prominently visible stars by day or night, in effect using nature as a global positioning system long before GPS was developed. When the autopilot was coupled to the ANS via the auto-nav function, the SR-71 could be flown automatically, adhering precisely to a predetermined flight path that was loaded pre-flight into the ANS's computer memory. To facilitate maximum mission flexibility, the SR-71 featured 3 interchangeable nose sections, housing either a high-resolution, side-looking radar, used for ground mapping and referred to as CAPRI, standing for Capability Reconnaissance Radar, an Advanced Synthetic Aperture Radar System, or ASARS, or a so-called glass nose housing a palletized optical bar camera, or OBC. The SR-71 did not carry any form of defensive weaponry save that which was generated electronically. ECM was and remains a highly sensitive area, where fast-moving technological advances meant that the SR-71's defensive electronic systems required continual updating throughout its operational life. Within the SR-71's cockpit, pressurization was allowed to fall steadily as the aircraft climbed from sea level to 8,000 feet, whereupon it remained constant to 25,000 feet. This ensured that the fuselage wasn't subjected to unduly high pressure gradients, which in turn meant that the aircraft's structural weight could be reduced. However, if pressurization was lost or the crew needed to eject, survival was dependent upon each of them wearing a full pressure suit. This requirement was reinforced by Air Force Regulation 60-16, which stipulated that full pressure suits must be worn when flying above 50,000 feet. In 1977, the company developed the next generation of pressure suits, designated the S-1030 series, and featured a high level of commonality between the U-2 and SR-71 programs. Colored old gold, the suit incorporated state-of-the-art textiles and was more durable and comfortable. Its 4 principal layers consisted of an outer coverall of Nomex that was durable, tear, and fire-resistant. The helmet, designated GN121394, was attached to the suit via a rollerball ring to enable the head to be turned. Oxygen was supplied to the crew members through holes situated around the helmet face seal. An airtight port located on the lower right side of the helmet enabled crew members to drink water via a straw to ensure they remain hydrated, and a level of sustenance was also available in the form of liquidized food dispensed from a tube. Gloves completed the pressure seal and were attached via wrist hinges. Boots featured heel retraction strips that were connected by cable to the ejection seat on entry to the cockpit. The complete pressure suit system cost about $130,000 a copy. Crews were issued with 2, and they lasted 10 to 12 years, undergoing a complete strip-down overhaul every 5 years and a thorough inspection every 90 days, or 150 hours. December 22nd. The first SR-71, with Skunk Works test pilot Bob Gilliand at the controls, took to the air for the first time. Departing from Lockheed's Air Force Plant 42, Site 2 facility at Palmdale, it remained airborne for just over an hour and reached a speed in excess of 1,000 miles per hour, which, Johnson noted, is some kind of record for a first flight. Though the SR-71 first flight had been completed with few difficulties, ongoing flight testing of the aircraft had not been comparably problem-free. The SR-71 flight test program, conducted at Palmdale, like that of its A-12 predecessor, was not without its accidents. The first, involving the third SR-71A, occurred on January 25, 1966, when Skunk Works pilot Bill Weaver miraculously escaped without using his ejection seat. His back sealer, Jim Zwire, was not so lucky and was killed. At the time of the accident, the aircraft was in a right turn, and the right inlet forward bypass doors were being controlled manually by Weaver. Though SR-71s finally were beginning to enter the operational Air Force inventory, the miscellaneous subsystem problems remained difficult to overcome. Tank sealing and range deficiencies continued to plague the aircraft, including those considered operational at Beale Air Force Base, and corrective action was painfully slow in overcoming them. By late 1967, all 31 SR-71s on order from Lockheed had been completed and delivered. By late September of 1969, the SR-71 was well on its way to a long and illustrious operational career. SAC already had flown well over 100 hot missions out of Kadena. NASA, for the first time, formally inquired into having an SR-71 for test purposes on December 29, 1970, when a query was received by the Skunk Works concerning possible use of the aircraft to launch test-scale models of the forthcoming space shuttles. On July 28, 1971, Johnson noted in the log, "Nothing new on the SR-71 operation. SAC made a 10-hour flight a short time ago on which about half the time was over Mach 3 and 80,000 feet. They flew 10,000 miles. The Vietnam War had successfully justified the SR-71's existence from the time of its operational debut during 1968 through 1973. Some 600 missions had been logged during the course of Vietnam operations, and the aircraft had logged an enviable record of dependability and mission successes. Temporary deployment to forward operating locations, or FOLs, worldwide were undertaken with considerable alacrity, and during the course of its service career, The aircraft overflew almost every major political and military significant hotspot in the world, gathering intelligence data of inestimable political and military value. The previously mentioned YF-12A speed and altitude records were eclipsed by the SR-71A during a series of Fédération Aéronautique International monitored flights during 1976. As of this writing, all of these records still stand, including the world's absolute speed and sustained altitude records. During the late 1980s, as major international political and economic changes began to manifest themselves throughout the world, the U.S. intelligence community began to reassess priorities, and in particular, the way it was going to spend its limited financial resources. Virtually every program, including the SR-71, was reviewed with the intent of determining its long-term viability and, in particular, its simple cost-effectiveness. As a result of this review, and in light of advances in other sensor system programs, on October 1, 1989, all SR-71 activities, with the exception of crew proficiency training and associated training flights, were suspended while the Air Force awaited release of the 1990 fiscal year budget. When revealed several weeks later, funding for the SR-71 program had been eliminated. Accordingly, all Air Force SR-71 operations were terminated officially on November 22nd.
Good evening. Recent budgetary cuts for the Air Force have ended funding for the SR-71 reconnaissance aircraft program. Local civilian and military personnel had the opportunity to view the final functional check flight of the SR-71 as it prepared to return to the United States.
Rolling down Kadeena's runway for one of the last times, the SR-71, nicknamed the Habu, performed a functional check flight in preparation for its last trip to the United States and into the pages of history. The atmosphere was charged with excitement as the flight crew, Major Jim Greenwood and Captain Steve Zaviniak, were assisted into 45 pounds of pressure suit. The physiological support technicians then conducted pressure tests on each suit and again performed these tests in the aircraft during pre-flight. The extra tests help ensure the suits will work in the event the pilots need to eject. The suits allow ejection at altitudes above 80,000 feet at speeds of Mach 3. After all pre-flight checks were done, the engines were started and the Habu came to life and soared into the skies of Okinawa for one of the last times. From Kadena Air Base, I'm Airman Rob Ivey.
Many of the Lockheed, Air Force, and CIA personnel who had been involved in the program during the preceding 24 years were on hand to say farewell to what many viewed as the single most significant military aircraft of the post-World War II period. To build Have Blue, we needed $10 million. One can't imagine what goes through your mind when you have to ask the board of directors to invest $10 million at a time when the corporation was considering declaring bankruptcy. The $10 million investment brought the company several billion dollars of sales and a reputation of technical superiority and stealth technology. The advantages of low observables, or stealth technology, have been a military matter of considerable interest for decades. Applicable not only to aircraft, but to all other forms of military equipment as well. Attempts to camouflage or reduce the visibility of hardware and personnel have been ongoing since the beginning of recorded military history. During World War II, the application of camouflage paint patterns was studied with considerable intensity. Scientifically conducted research helped generate patterns that genuinely reduced an aircraft's visibility both in the air and on the ground. Polished aluminum, for instance, was criticized for its notable ability to reflect sunlight and increase the detection distance of a target aircraft. Dull, non-glare matte-type paints eliminated the problem, but not without increased expense and some cost in performance. The exigencies of war curtailed extensive research into the development of airworthy, non-radar reflective structural materials, but some attempts were nevertheless made. The Germans, in particular, placed emphasis on lowering the radar return of select aircraft, including the notable O-229. This extremely advanced all-wing jet fighter, built primarily of wood over a steel tube load-bearing structure, in some production models was to have utilized a wood sandwich ply with a core material of granulated charcoal. Presumed to have absorbed radar energy, the charcoal was calculated to reduce the aircraft's radar return by a not insignificant margin. The war ended before the technology could be fully exploited. Countermeasures were slow to develop initially, with little focus on reducing radar visibility or countering radar energy during the 1950s and 1960s. It wasn't until the Vietnam War that effective electronic countermeasures were pursued. The threat of radar-guided missiles required a reassessment of technology, leading to the development of ECM pods and chaff dispensers. Lockheed gained experience in anti-radar features through programs like the U-2, A-12, and SR-71. In 1974, DARPA requested studies for a low observable fighter, excluding Lockheed, but they were eventually included through the Skunk Works efforts. Lockheed refined external shaping techniques using Echo 1, a computer program predicting radar cross-sections, or RCS, based on mathematical formulas. They employed faceting, creating a three-dimensional aircraft from flat panels to reduce RCS. Validation testing was conducted with a model called the Hopeless Diamond, demonstrating lower RCS than previous designs. In August of 1975, Lockheed, along with Boeing and Northrop, received invitations from the Defense Advanced Research Projects Agency to participate in a highly competitive project known as the Experimental Stealth Test Bed. The objective of this project was to develop and test an innovative aircraft design with exceptional low observability characteristics. After a thorough evaluation process, Lockheed was selected in April 1976 to proceed with the detailed design, development, and testing of the aircraft, which was named Have Blue. A single-seat subsonic aircraft featured a distinctive design aimed at achieving both high maneuverability and low observability. A significant feature of the aircraft was the inclusion of a large two-position flap known as the platypus, which automatically deflected downward when the angle of attack exceeded 12 degrees, enhancing the nose-down pitch control. The initial engine runs were accomplished on the first Have Blue aircraft on November 4, 1977, at Lockheed's Burbank facility. In order to maintain security, the aircraft was parked between two semi-tractor trailers over which a camouflage net had been installed. On December 1, 1977, with Lockheed test pilot Bill Park at the controls, Have Blue lifted into the air. A new era in military aviation had just begun. Only 20 months had passed since contract award. As previously noted, the primary objective of the test program was to demonstrate VLO technology. Towards this end, Have Blue 1001 would demonstrate loads flutter, performance handling qualities, and stability and control. Have Blue 1002 was designated as the PCS test vehicle. Have Blue 1001 accomplished 36 flights over the next 5 months and successfully expanded the flight envelope sufficiently to allow the RCS testing to be performed. Have Blue 1002 joined the program during 1978 and flew for the first time on July 20th with Air Force pilot Norman Ken Dyson at the controls. This aircraft differed from Have Blue 1001 in that it possessed a real airspeed system and did not have a drag chute installed. It also incorporated nose wheel steering to improve ground handling and was adorned with all the coatings and materials required to perform its intended task. Following some airspeed calibration flights, the aircraft accomplished 52 flights during the next 12 months and completed the low observable testing. The final phase of testing in a simulated integrated air defense environment was completed during July of 1979. The aircraft demonstrated its low observable capabilities against ground and airborne systems during these tests. Its low acoustic signature was also verified. The Have Blue program was a low-cost demonstration of a radically new concept in VLO aircraft design. Have Blue program accomplishments included, from a technical standpoint, lowest RCS aircraft in the world by several orders of magnitude, VLO infrared signature, VLO visual signatures, VLO acoustic signature, and confirmation of complex aerodynamics. In conclusion, it was determined VLO tactical and strategic aircraft could be designed, produced, and operated. I always felt it would perform very well, but I never expected it to perform as well as it did. We had not involved the airplane operationally, and therefore the operators didn't know how to use the airplane. It's like having a new tool. I was worried we hadn't operated it enough. On the evening of January 16th, 1991, television viewers who tuned into CNN witnessed a rare live preview of future wars. Correspondents Bernard Shaw and Peter Arnett, broadcasting from the room in Baghdad's Al-Rashid Hotel, reported on Iraq's state of alert under Saddam Hussein.
This is something is happening outside. Peter Arnett joined me here. Let's describe to our viewers what we're seeing. The skies over Baghdad have been illuminated. We're seeing bright flashes going off all over the sky. Peter?
Well, there's anti-aircraft gunfire going into the sky. However, we have not yet heard the sound of bombs landing, but there's tremendous lightning in the sky.
I have a sense, Peter, that people are shooting towards the sky, and they are not aware or cannot see what they're shooting at. This is extraordinary. We're getting starbursts, seeming starbursts in the black sky. We have not heard any jet planes yet, Peter.
No plane. Now the sirens are sounding for the first time. The Iraqis have informed us.
5.5 months after Iraq invaded Kuwait and 17 hours past the coalition's withdrawal deadline, Baghdad was shielded by the world's densest air defenses. This included 76 surface-to-air missile launchers, or SAMs, and nearly 3,000 anti-aircraft artillery guns. Iraqi radar operators scanned the moonless sky for signs of incoming aircraft, but saw nothing. Shaw remarked, "We haven't heard any planes yet," speculating if the B-52 bombers flew too high to detect. 650 miles to the south, at Khamis Musheit, in southwestern Saudi Arabia, U.S. Air Force pilots of the 37th Tactical Fighter Wing were also glued to CNN's broadcast. 2 hours earlier, some of their squadron members had taken off from King Khalid Air Base for the war's first airstrike. One of their objectives, located on the west bank of the Tigris River, was the 370-foot Al-Kark communications tower, which transmitted CNN's signal to the outside world. As the estimated time of the strike neared, everyone at King Khalid kept one eye on CNN and one on their watch, counting down. If all went as planned, the network would go dark. Now. The need for an aircraft capable of penetrating modern air defense systems had actually emerged from another Middle Eastern conflict almost 20 years prior. During the 1973 Yom Kippur War, Israeli-flown McDonnell Douglas F-4 Phantoms were heavily impacted by Egypt's radar-guided SA-6 SAMs. At the same time, in Vietnam, the U.S. Air Force was dedicating more than half its aircraft to radar suppression instead of bombing. The first real solution to these challenges came in 1975 from the most likely source, Lockheed California's Advanced Projects Division, the renowned Skunk Works. Engineers there realized that curved surfaces reflect energy in multiple directions, like how a soap bubble reflects sunlight. However, if an aircraft had flat surfaces, like the facets of a diamond, reflections could be directed away from the enemy receivers. Faceting led to handling difficulties for pilots, prompting Skunk Works team leader Ben R. Rich to secure government funding for 2 full-sized prototypes under the purposely vague codename Have Blue. Because the aircraft provided near immunity to radar, the Air Force quickly funded the production of full-scale development, or FSD, models. The new design incorporated lessons from the Have Blue program, including increased engine power. The inlets and exhausts were baffled and soundproofed. Reducing noise instead of the typical jet turbine roar, the plane emitted a high-pitched whine that could set dogs barking before it even appeared. The inward-canted fins of the prototypes had reflected heat emissions, so the FSD models featured outward-canted fins in a V-shaped butterfly tail. Combat requirements modified by the need for stealth influenced the rest of the redesign. Unlike most military aircraft since the 1950s, the plane carried no radar, as even an inactive radar acts as a reflector. Even the standard radio antennas found on conventional aircraft were designed to retract beneath the plane's surface when not in use. Additionally, since external fuel tanks and weapons would negatively impact the plane's radar cross-section, or RCS, all fuel and munitions were stored internally. Over the next decade, the stealth fighter, as it was popularly known, became a major topic of discussion in the aviation world. The new aircraft was assigned the code name Senior Trend and the misleading designation F-117. Test flights were mostly conducted at night, scheduled to avoid detection by Soviet reconnaissance satellites. The Nellis Range, also home to the Air Force's Red Flag air combat exercises involving American and Allied military aircraft, maintained a security screen to keep the other aircraft away from the Groom area. Despite the F-117 being 33% larger than the prototype, its radar cross-section, or RCS, measured between 0.01 and 0.001 square meters, roughly equivalent to that of a small bird. This allowed the F-117 to approach ground-based search radars 90% closer and airborne radars 98% closer before detection. Testing was still ongoing when the Air Force ordered a full wing of the production version of Senior Trend, designated the F-117A Nighthawk. The first military pilot to fly a Nighthawk was Lieutenant Colonel Alton C. Whitley, a Vietnam veteran with combat experience in the A-7 and North American F-100, and a former commander of the Air Force's Aggressor Squadron. He recalled, "When I first looked at the F-117A, it reminded me of some Star Wars type of aircraft. I thought, boy, is this the 21st century." Normally, the Nighthawk's fly-by-wire system managed its instability so well that when one jet lost an entire rudder at high speed, the pilot only learned of it from the chase plane, yet landed safely. With low wing loading and G limits comparable to the F-4, the F-117 reportedly handles well. The wildly publicized nickname Wobbly Goblin stems from its departure characteristics. Once it loses control, recovery is nearly impossible. In June 1986, and again in October 1987, Nighthawks crashed into the ground due to pilot fatigue and disorientation. Despite efforts by the U.S. Air Force to keep these incidents under wraps, news leaked out. In November 1988, the Pentagon publicly disclosed a grainy, retouched photo that revealed very little of the F-117. Twice, stealth fighters were on the verge of bombing targets in Libya, but the missions were canceled to maintain secrecy. It wasn't until December 1989, during Operation Just Cause, the U.S. invasion of Panama, that the F-117A saw its first combat. During the operation, 6 Nighthawks flew to Panama via Texas and the Caribbean Sea, with 2 serving as backup aircraft and turning back unneeded. 2 others were assigned to support special forces attempting to capture General Manuel Noriega, but that mission was canceled. Confusion over a last-minute change led to a mix-up regarding the remaining target, a barracks housing 2 battalions of elite enemy troops. The goal was to stun rather than kill. The lead F-117A achieved this with a single 2,000-pound Mark 84 bomb. Known colloquially as the Hammer, the bomb, capable of a lethal radius of 400 feet and blowing out eardrums half a mile away, exploded in a field beside the barracks, causing significant confusion among the Panamanians. The second stealth jet also hit its target, although it was the wrong location. Nonetheless, the Air Force deemed the mission successful, as the stealth jets remained undetected by Panamanian radar. On August 17, 1990, Colonel Al Whitley took command of the 37th Tactical Fighter Wing. 4 hours later, he recalls, the word came in to deploy our first squadron. The U.S. and its allies planned to remove Saddam Hussein's forces from Kuwait. King Khalid Air Base, located 6,500 feet up in the mountains near the Red Sea and nicknamed Tonopah East, had been constructed in the late 1970s in exchange for delivering McDonnell Douglas F-15 Eagles and AWACS airborne radars to Saudi Arabia. Because the base was beyond the range of Iraqi Scud-B missiles, the stealth jets required 3 mid-air refuelings to reach their primary target, downtown Baghdad. I generally put the F-117s against the Baghdad targets, said the Air Force's chief mission planner, Brigadier General Buster C. Glosson, where we would have lost conventional airplanes. The mission team included only 3 combat veterans, Whitley, his deputy commander, and 1 pilot from Operation Just Cause. However, after 5 months of intense training over the barren Nevada desert, the Night Stalkers and Ghost Riders were ready. They carried 2 tons of bombs, each over more than 1,000 miles of desert at night. Shortly before 3 a.m., local time on January 17, 1991, 8 stealth jets arrived above Baghdad with lights off and radio silent. Captain Marcel Kerr-David was tasked with bombing the Al-Kark Tower. Even though I felt very well prepared with my training, I was somewhat apprehensive about the aircraft. He later admitted, its stealthiness had not been tested in combat, and everyone wondered whether or not this stealth stuff really worked. Does the U.S. military have a new black aircraft program in development? Since the mid-1980s, the aviation press has been scrutinizing Pentagon documents and eyewitness accounts, suggesting a new stealth fighter for the next century. In February 1985, the Pentagon budget request accidentally listed a project alongside Lockheed's SR-71 Blackbird and U-2 spy planes, under the code name Aurora. This may have been a ruse similar to the F-19 ploy, as Aurora was also a name for a maritime patrol aircraft developed for the Canadian military. However, While the Canadians received their Auroras, the Pentagon's Aurora project reportedly continued, with funding rising from $80 million in fiscal 1986 to approximately $2.3 billion by 1987. Typically, the Air Force had no comment on the matter. However, by 1988, it was rumored to be working on a replacement for its SR-71 reconnaissance aircraft, which it retired with surprising eagerness in March 1990. Artistic renderings, some perhaps intentionally misleading, depict Super Blackbirds weighing over 150 tons, powered by variable cycle turbo ram rockets burning liquid methane or hydrogen, cruising the edge of space at Mach 6. Eyewitness accounts suggest that Aurora, if it exists, is more modest in size, but not necessarily in performance. In early 1990, Aviation Week and Space Technology reported unusually loud nighttime air traffic over Edwards Air Force Base in California, with one source describing the noise as the sky being ripped open. In June 1991, a sonic boom similar to those produced by space shuttles re-entering the atmosphere and strong enough to be detected by seismographs rumbled across Southern California. Judging by its sonic footprints, the object was flying toward the vast Nellis Air Force Range at speeds exceeding Mach 3. Activity seems to be concentrated around the remote Machrihanish Air Base in western Scotland, which was linked to the F-117A before the Nighthawk was publicly known. In November 1991, a Royal Air Force air traffic controller reportedly saw a radar blip leave Machrihanish traveling at Mach 3. Additionally, in August 1989, an engineer on an oil rig in the North Sea witnessed a mid-air refueling operation involving a mysterious aircraft shaped like an isosceles triangle when viewed from below. One thing is certain: design teams like the Skunk Works are always pushing the boundaries of innovation. Anticipating a barrage of anti-aircraft fire, mission planners assigned a second stealth jet to mark Kerdavid's target and reduce his workload. As the laser beam illuminated the dome-shaped roof of the Alcarc, a forward-looking infrared radar, or FLIR scope, in Kerdavid's plane detected the signal and displayed it on the cockpit's 8-inch video screen. Using a fingertip control on his throttle stick, Kerdavid locked his aim point onto the laser reflection, and his weapons system projected an imaginary basket above it, guiding where the bomb needed to be dropped for a successful strike. 10 seconds before release, Kerdavid pressed the pickle button to activate his weapons system. The Nighthawk's bomb bay doors opened, and its lethal payload, a 1-ton GBU-27AB guided bomb specifically designed for the F-117A, was released into the slipstream. With the threat of anti-aircraft fire mitigated, Kerdavid, who was later awarded the Silver Star for his action, dropped his bomb from a relatively high altitude and close to the Alcarc. He then veered north towards his secondary target, a command bunker in the Taji suburbs. Meanwhile, the second F-117 remained on station briefly, using its belly-mounted downward-looking infrared radar, or DLIR, laser designator, to mark the target for Kerdavid's bomb as it descended. In their room at the Al Rashid Hotel, CNN reporters picked up the sound of an air raid warning. "Now the sirens are sounding for the first time," Peter Arnett noted. "The Iraqis have informed us." At that moment, as if from nowhere, Kerdavid's GBU-27 struck the Alcarc Tower, drilling halfway down before detonating. The building split in half, an event missed by CNN viewers and personnel at King Khalid as the network immediately went offline. An audio-only land link allowed Peter Arnett to describe the blinding spray of aimless return fire rising above the Baghdad skyline, while the Iraqi gunners' radars showed no aircraft above them. Seconds later, another F-117A's GBU-27 hit directly across the Tigris from the Al-Qarq. It penetrated the roof of the 12-story Baghdad International Telephone Exchange, known to Air Force mission planners as the AT&T building, the only target in the city scheduled for a double hit. Major Jerry Leatherman of the 415th Tactical Fighter Squadron, one of those planners, circled in from the northeast 60 seconds after the first strike. He dropped 2 high-blast Mk-84 bombs from 3 miles up through the hole in the building's roof. The first bomb landed slightly low, but the second hit perfectly, together demolishing the top 4 floors. In rapid succession, 3 waves of stealth jets struck their targets with a precision that was both merciful and ruthless, targeting the Iraqi Air Force and Ba'ath Party headquarters, air defense control centers, Rashid Airfield, and other high-value objectives, including 2 of Saddam Hussein's presidential palaces. Within half an hour of the initial strikes, Baghdad went dark, likely due to the destruction of the power grid rather than Iraqi countermeasures. Despite the blackout, the city remained illuminated by the persistent anti-aircraft fire. Back at King Khalid, ground crews anxiously counted the returning aircraft, with the last arriving only after dawn. Remarkably, every Nighthawk returned safely without a single scratch. In the first 24 hours of the war, the 42 stealth fighters at King Khalid, just 2.5% of the total Allied aircraft deployed in the Gulf, were responsible for 31% of the targets attacked. Damage estimates were lower than anticipated, partly due to a low mist obscuring Baghdad at dawn. Additionally, the cloud cover, which was 3 times the seasonal average during the war, not only interfered with subsequent operations, but also compromised the jet's stealth capabilities. If you're just above a cloud deck with the moon reflecting off it, you can really stick out, explained Leatherman. At one point, an F-117A was shadowed by what seemed to be an Iraqi Dassault Mirage F-1 fighter, which was shining a landing light or spotlight to visually acquire the stealth jet. A slight maneuver, however, broke the lock, making it the closest any Nighthawk came to a dogfight over Iraq. Throughout the Gulf War, the Black Jets were consistently tasked with the most perilous, high-priority targets. These included radar sites, SAM and Scud launchers, enemy command control communications facilities, bridges, hardened aircraft shelters, and bunkers. Their data recorders captured some dramatic video footage for Air Force publicists. Notable examples include a hardened Scud storage facility destroyed by a laser-guided bomb dropping through an air duct, a bomb blowing in the door of an ammunition bunker followed by another bomb exploding inside, and a GBU-27 descending an elevator shaft to detonate deep within the Iraqi Air Force headquarters, demolishing all 4 walls. Ultimately, the F-117A Nighthawk's precision strikes played a crucial role in minimizing collateral damage and saving lives on both sides during the Gulf War. By successfully handling more than 40% of the coalition force's strategic targets, the Nighthawks demonstrated the effectiveness of stealth technology and precision bombing. The success of the F-117A led to significant changes in U.S. Air Force tactics and technology post-war. The 37th Tactical Fighter Wing, redesignated the 49th Tactical Fighter Wing, relocated from Tonopah to Holloman Air Force Base, New Mexico. Air Force analysts have so far found no way stealth technology can be compromised in the foreseeable future. In any case, the F-117A Nighthawk, the Skunk Works, and Ben Rich are assured their places in aviation history. We guaranteed to deliver an aircraft which would have stealth characteristics, be virtually undetectable by today's known radar technologies, and be able to deliver a weapons system with unprecedented accuracy, said Rich. We've done that. Our accomplishments speak for themselves. In many ways, the F-22 Advanced Tactical Fighter is the true daughter of the F-117. Stealth will be a major factor in the USA remaining a superpower in the 21st century. We worked very hard with the F-22 to integrate stealth into a supersonic, supermaneuverable fighter, and we succeeded. After our last day of YF-22A flight demonstrations from Edwards late on December 28, 1990, I said to my wife, Judia, we won. And we did. Our team delivered results. It was a privilege to lead this team. The F-22 Raptor is the most advanced aircraft of its kind, designed around the principles of first look, first shot, first kill. It is set to become the primary air superiority fighter for the U.S. Air Force in the 21st century. The Raptor, as its name suggests, is a lethal machine. As menacing as it appears, it is even more deadly when deployed for its missions. Deadly and undetectable from long distances. This stunning fifth-generation fighter combines unparalleled dogfighting abilities with precise ground attack capabilities. Confidence in these objectives stems from a synergistic blend of features and capabilities, including stealth technology, the ability to cruise at supersonic speeds over long distances without afterburners, and an integrated, highly sophisticated avionics suite. The FA-22A has been designed to be more maneuverable, better armed, more reliable, easier to maintain, more readily supportable, and more capable in air-to-ground missions than any other comparable aircraft in history. Throughout the 1960s and 70s, the Soviets developed various missiles to attack at different altitude bands, making it impossible to fly under or over the missile threat. You had to confront it directly. One way to address this was to prioritize the suppression of enemy air defenses, specifically by destroying missile sites and their radars as the most crucial mission for the Air Force. By the 1970s, air superiority had once again become a top priority, leading the U.S. Air Force to commit to building its first pure air superiority fighter, which would eventually become the F-15 Eagle.
I have never seen a finer joint government-industry team that's organized with the technical competence to carry out the job that's been assigned to them, or to do it in a manner of close-knit teamwork.
However, just as the F-15s became operational in 1978, alarming new evidence suggested that their superiority might be short-lived. At the same time, and perhaps most importantly, reconnaissance satellites photographed several new fighter prototypes, the Mikoyan MiG-29 and Sukhoi T-10, at the Ramenskoye Flight Test Center near Zhukovsky, about 40 miles southeast of Moscow. The new generation represented a significant improvement in capability over anything previously observed by U.S. intelligence services. It was clear to everyone involved that a new air-to-air combat platform would be necessary to counter the threat posed by these new Russian aircraft. The Sukhoi T-10 was a huge shock to Western analysts. It was larger than the F-15 and far bigger than any previous Soviet-built fighter. If the MiG-29 had already concerned the American military establishment, the existence of the Sukhoi T-10 set off alarm bells. These aircraft were highly advanced, capable of competing with some of the top NATO fighters like the Phantom and ultimately the F-15. Just weeks into his first term, America's 40th president increased U.S. defense spending by $32.5 billion, initiating a massive rearmament of the United States.
One that I mentioned earlier. It is absolutely essential that we increase our spending
for national defense if we're to preserve the peace.
In 1981, the Cold War was heating up. As Reagan and Brezhnev faced off, the U.S. Air Force concluded that it urgently needed a replacement for its F-15, an Advanced Tactical Fighter, or ATF, that would have no equal. As American planners began developing the concept of air-land battle to prepare for a potential World War III, the U.S. Air Force started considering the type of equipment it would need for such a conflict. On August 24, 1982, a Program Management Directive, or PMD, was issued, changing the program element's name from Combat Aircraft Technology to Advanced Tactical Fighter. Concurrently, two sub-projects were established under this banner. The Advanced Tactical Fighter, which included concept and technology development, 7 airframe companies, Boeing, General Dynamics, Grumman, Lockheed, McDonnell Douglas, Northrop, and Rockwell. Each received $1 million concept development investigation contracts. And the Joint Fighter Engine, an engine technology demonstration program managed jointly with the U.S. Navy. Pratt & Whitney and General Electric each received contracts valued at $202 million in September 1983. Other companies contending for the contract included Allison, Garrett, and Teledyne CAE. The 7 competing companies submitted a total of 19 conceptual designs, ranging from Northrop's lightweight cooperative fighter, smaller than an F-16, to Lockheed's battlecruiser, based on the design of their short-lived YF-12A long-range interceptor. Additionally, an in-house design, a subsonic low observable fighter, was submitted by the Air Force's Flight Dynamics Laboratory, or AFFDL. Of the approximately 19 studies submitted, 4 were eventually chosen to represent different mission philosophies. A very light, austere, low-cost design, a supersonic cruise and maneuver design, a subsonic, low observable design, and a high Mach, high-altitude design. From these, it was concluded that the ideal air-to-air platform would combine low observability with super cruise and superior maneuverability. The platform would, in turn, offer reduced vulnerability to surface-to-air missiles, while nearly eliminating exposure to anti-aircraft, artillery, and other short-range systems. The Red Baron study, which analyzed air-to-air combat in Vietnam, had sparked the race for stealth technology. An operational analysis of the Vietnam War showed that most aircraft were shot down by enemy aircraft they had not seen. This highlighted the significant advantage of being undetected in air combat. Air combat data from World War II and Korea reinforced the need for invisibility. The principle of stealth technology is to make an airplane virtually invisible to the enemy. An aircraft's shape must reflect incoming radio waves away from enemy radar rather than towards it. To further enhance low observable characteristics, an airplane is covered in materials that absorb radar signals, further reducing its visibility on a radar screen. Leading the way in stealth technology was Lockheed's Skunk Works. In 1977, amid unprecedented security, Lockheed had flown a prototype of the world's first stealth fighter. By the 1980s, during Operation Just Cause, its F-117 had helped to dismantle General Noriega's regime in Panama. Now, the U.S. Air Force decided that any new fighter must incorporate stealth technology and identified 2 other areas in which a future air superiority fighter should excel. The challenge was issued, and it was up to the finest aviation manufacturers in the world to respond. The Advanced Tactical Fighter program was about to begin, and the Raptor, America's 5th-generation fighter, was about to be hatched. By 1983, U.S.-Soviet relations had reached a new low. Following Leonid Brezhnev's death, the Politburo, now controlled by former KGB boss Yuri Andropov, was labeled by Reagan as the focus of evil in the modern world. Continuing his policy of rearmament, Reagan announced plans for the Strategic Defense Initiative, better known as Star Wars, prompting a furious reaction from Moscow. In August, when Korean Airlines Flight 007, on its way to Seoul from New York, strayed several hundred miles off course into Soviet airspace, Russia responded. A fighter was dispatched, and the civilian airliner, with 269 people on board, was shot down. The shooting down of KAL-007 sent shockwaves around the world, straining international relations to the breaking point. Reagan's reaction to the crisis strengthened U.S. conviction that stealth would now be the prime requirement for America's new fighter.
I'd like to talk for a moment about why we're developing a new fighter at this time. There's probably not a person in this room or in the reach of your television cameras who isn't aware of the contribution of stealth to our success in Desert Storm. In that case, it was a bombing capability that we were seeing in action. But the principle will apply to both ground attack and air-to-air missions in the future. The ATF is intended to replace the aging F-15 Eagle, currently our frontline fighter. The Air Force's F-15s are outstanding aircraft, and they swept the skies in Desert Storm. However, when the ATF is first deployed, the F-15s will be over 25 years old. Several other aircraft, including some we faced in Desert Storm, are aerodynamically competitive today with the F-15 and other leading U.S. fighters. We win today with an edge in avionics and by relying on the superior skill and training of our pilots. Others will try to close that gap between now and the year 2002, when the first ATF squadron is fielded. The ATF will balance stealth, supercruise, and advanced avionics in a highly maneuverable fighter that will ensure that our pilots get first look and first kill. Thus, the ATF will ensure American air superiority well into the next century. As we have seen in Desert Storm, air superiority is essential to effective air and ground operations. American ground forces have not had to fight without air superiority since 1942, and we plan to keep it that way as well.
Following 4 initial drafts, the basic framework for the ATF requirement was released to the industry. The framework called for a radius of action of approximately 800 miles, supersonic cruise capability of 1.4 to 1.5 Mach, a 2,000-foot runway requirement, a gross takeoff weight of 50,000 pounds, and a unit cost of no more than $40 million in 1985 dollars. Importantly, the proposal implied that the ATF life cycle cost, or LCC, the aircraft unit cost upon delivery plus the cost of all spares, fuel, maintenance, and flying, should be at least as good as, if not better than, the McDonnell Douglas F-15. It was concluded that the submissions from Lockheed and Northrop were superior to those from Boeing, General Dynamics, and McDonnell Douglas. Each manufacturer would submit a design for the demonstration evaluation, or DEMVAL competition, with the understanding that the winning company would be the prime contractor, and its partners would be subcontracted to produce major components. Lockheed, whose initial design studies had been considered frontrunners during the early ATF reviews, had begun consortium discussions with Boeing and General Dynamics as early as June 1986. A public announcement was made on July 2nd, but did not formalize an agreement with its partners until the following October 13th. Consequently, Lockheed assigned Sherman Mullins as general manager for the ATF Team Program Office. Mullen would lead Lockheed in the prime contractor role, leveraging the unique technical strengths of Boeing and General Dynamics. 2 weeks later, Northrop followed suit by leading a team with McDonnell Douglas. In response to these teaming decisions, revised proposals from all 7 airframe contractors were submitted on July 28, 1986. By default, the two consortia were selected on October 31st, 1986, to build two prototypes each for the revised demonstration and validation phase. Lockheed, under a $691 million contract, would build two of what later became its Model 1132, initially referred to as Configuration 092, under the official Air Force designation YF-22. Northrop, under a similar $691 million contract, would build two of its N-14 proposal under the official Air Force designation YF-23. At the end of the process, one of these designs would become America's new advanced tactical fighter. Costing billions of dollars, the new fighter aimed to make a significant technological leap into the 21st century. Just 9 months after being selected to build the demonstration and validation fighters for the U.S. Air Force, Lockheed shocked everyone by scrapping its original design. In a hectic 3-month process, with help from its partners, Lockheed produced a completely different configuration featuring a clipped delta wing. Over the next 4 years, at a cost of just over $2 billion, America's tactical fighter competition became the largest program of its kind. In 1990, just months after the disintegration of the Soviet Union, the shapes of the two rival designs were finally unveiled. Northrop's version, called the YF-23, closely resembled its original design. In contrast, Lockheed's design, called YF-22, appeared surprisingly conventional, featuring 4 tail surfaces, vectored thrust, a broad solid body, and a conventional wing. Unlike Lockheed's other stealth aircraft, the F-117, radar-absorbent materials were not applied over the entire FA-22, but used selectively on its edges, cavities, and critical surface areas. The F-22 carries its weapons internally. 4 weapons bays are hidden in the central mid-body section. 6 missiles can be carried in the ventral bays, which are covered with bifold doors. The side bays each hold one Sidewinder missile on a trapeze launcher. The mid-body section also houses the fighter's landing gear and complex inlet ducts. Attached to the mid-body is the forebody, which accommodates the cockpit and advanced avionics. Both the YF-23 and the YF-22 are impressive-looking machines, but their performance still needs to be tested. The most crucial stage of the competition is still to come: the flight testing. Northrop was first in the air. In August 1990, flown by Paul Metz, the YF-23 got airborne. The test was a huge success, but Lockheed was quick to respond. On September 29th, at Edwards Air Force Base in California, Lockheed Chief Test Pilot Dave Ferguson prepared the Raptor for its maiden flight. Over the next 3 months, the Raptor underwent a series of rigorous tests. The Air Force required both teams to provide performance projections, which would then be compared with the actual performance of the airplanes in various conditions, including subsonic and supersonic flight at different altitudes. The winner of this stage would earn a contract for 650 aircraft. The decision would hinge not just on what the contractors promised, but on the Air Force's confidence in their ability to deliver. During flight testing, the Raptor outperformed the Northrop YF-23 in several crucial performance areas. The YF-22 had clearly demonstrated that in every category it was far superior to any existing fighter. But it would be events in 1991 that would carve out the Raptor's future.
2 aircraft you see here, or you've seen in action in the flying prototypes, I think are an excellent demonstration of exactly what we were trying to accomplish with this demonstration validation front end and the prototyping and hardware demonstration, including the avionics test beds that went along with that. We ended up with 2 aircraft, each one of which could meet the Air Force's technical specifications and technical requirements. And that's why, as I said in the formal remarks, that we had here a set of proposals or a set of contract options, any one of which was in the acceptable range and any one of which could have been selected. So we were dealing with shades of differences. Given that all of the proposals were in the acceptable range, we had to make the evaluation based on the criteria that were called out in the RFP, and we've done that, and the best I can do for you today is to report the final judgment of that process.
22 minutes after midnight on January 17, 1991, Lockheed's stealth F-117 spearheaded U.S. strikes against Saddam Hussein's regime. The performance of Lockheed's stealth bombers during Operation Desert Storm gave the company and its aircraft priceless publicity. However, another aircraft also emerged from the Gulf War with a glowing reputation. The F-15, the aircraft destined to be replaced by the ATF, emphatically confirmed its status as the foremost air superiority fighter in the world. Now it appeared that the need for an advanced stealth fighter, the F-22, might be unfounded. But not everyone agreed. By April 1991, bogged down by the F-15 debate, the U.S. Air Force prepared to announce the winner of the Advanced Tactical Fighter contract. Would the Raptor emerge from the controversy unscathed? After the DEM-VAL flight tests of the prototypes, Secretary of the Air Force Donald Rice announced that the Lockheed team and Pratt & Whitney were the winners of the ATF and engine competitions.
The DEM-VAL phase has accomplished the risk reduction and the design trade-offs that are its purpose. Its success is demonstrable in the excellent performance of the prototypes and the quality of the proposals from the contractor teams. To ensure the fairest possible evaluation of these outstanding designs and development teams, the evaluation process that we've been through has been intensive, thorough, and professional. That evaluation was conducted by Air Force and Navy teams, by a team involving both Air Force and Navy personnel, included not only the developer community, but users, testers, contracts experts, cost analysts, and all who would be involved in the next phase of development. The success of the demonstration validation phase and this formal evaluation process is also demonstrated by the fact that the evaluators were able to bring to me as the source selection authority 4 awardable contracts, each of which represented acceptable proposals that met Air Force requirements. However, in evaluating the engine and airframe proposals, one combination clearly offered better capability with lower cost, thereby providing the Air Force with a true best value. With all that said, I now announce that the ATF team will be composed of the Pratt & Whitney company who designed the F-119 engine, which will be integrated into the F-22, designed by Lockheed, team with Boeing and General Dynamics.
The YF-23 design was considered stealthier and faster, while the YF-22, with its thrust vectoring nozzles, was more maneuverable, as well as less expensive and risky. Having won the contract, Lockheed announced that it would locate the F-22's headquarters in Georgia, where the Raptor's forward fuselage would be built. General Dynamics would construct the F-22's mid-body section in Fort Worth, Texas, and Boeing would manufacture the wings and tail in Seattle, Washington. Follow-on work with the aircraft took place at Edwards Air Force Base, involving an additional 100 hours of flying time, approximately 25 flights, to expand the YF-22A's flight envelope and explore specific segments in greater detail. However, on April 25, 1992, the program encountered its first major setback. During preliminary testing, a YF-22, flown by Tom Morgenfeld, crashed shortly after takeoff. The aircraft hit the runway with the landing gear retracted, skidded approximately 8,000 feet, and caught fire. A key element of the Raptor's design, Thrust vectoring uses movable exhaust nozzles to adjust the angle of thrust from the two Pratt & Whitney engines. As the Raptor made its low-level flyby, Tom Morgenfeld kept the stick forward to keep the nose down. However, as the landing gear was retracted, the thrust vectoring engaged, pushing the aircraft towards the tarmac. The pilot struggled to correct this sudden change in direction as the Raptor began to veer off course. Despite the loss of the stealth aircraft, the program had achieved its major goals. 10 million man-hours of analysis, 4,000 hours of radar testing, and hundreds of hours of flight testing had gone into the aircraft's development, even before construction began. In fact, the F-22 had undergone more flight testing than any other fighter before full-scale production. On April 9th, the first F-22A, officially named Raptor, an earlier attempt to name the aircraft Superstar failed in 1991, was unveiled in a public ceremony at Lockheed Martin's Marietta, Georgia facility. Air Force pilots would soon have the opportunity to evaluate the new aircraft themselves. First flown by the Air Force in 1997, pilots at Edwards Air Force Base surpassed 2,000 flight test hours in over 900 missions. One of the key advances in the Raptor's design is its advanced cockpit and integrated avionics system. Key mission systems include the Sanders General Electric Electronic Warfare System, the Martin Marietta Infrared and Ultraviolet Missile Launch Detector, the Westinghouse Texas Instruments Active Electronically Scanned Array Radar, the TRW Communication, Navigation, Identification Suite, and the Long Range Advanced IRST currently being tested. The electronic support measures systems radio frequency receivers give the aircraft the ability to perform intelligence, surveillance, and reconnaissance tasks. The F-22 features a glass cockpit with all digital flight instruments. The monochrome head-up display offers a wide field of view and serves as a primary flight instrument, while information is also displayed on 6 color liquid crystal display panels. The ejection seat in the F-22 is a version of the ACES II in U.S. Air Force aircraft, featuring a center-mounted ejection control. The F-22 is equipped with a sophisticated life support system, including an onboard oxygen generation system, protective pilot garments, and a breathing regulator anti-G valve that controls the flow and pressure to the pilot's mask and garments. The Raptor carries a formidable array of ordnance. It has 3 internal weapons bays, a large main bay located on the bottom of the fuselage, and 2 smaller bays situated on the sides of the fuselage, aft of the engine inlets. The main bay is divided along the center line and can accommodate 6 launchers for beyond visual range missiles, while each side bay contains a launcher for short-range missiles. The primary air-to-air missiles are the AIM-120, AMRAAM, and the AIM-9 Sidewinder, with plans to integrate the AIM-260 JATM in the future. Missile launchers require the bay doors to be open for less than a second. During this brief time, pneumatic and hydraulic arms push the missiles clear of the aircraft to minimize detection and allow deployment during high-speed flight. Although the F-22 typically carries its weapons internally, the wings feature 4 hardpoints, each rated to handle 5,000 pounds or 2,300 kilograms. Each hardpoint can be equipped with a pylon capable of carrying a detachable 600-gallon, or 2,270 liters, external fuel tank, or a launcher holding 2 air-to-air missiles. In addition to its armament of 8 missiles, the fighter is also equipped with a gun. At one point during the evolution of the Advanced Tactical Fighter program, the U.S. Air Force considered eliminating the gun to save weight. By the late 1990s, pilots involved in the Raptor program were confident that their aircraft could easily outperform and defeat any other fighter. This confidence, however, was based primarily on controlled flight and missile firing exercises. What these pilots truly needed was combat experience, and they were about to get it. The F-22 is equipped with an internally mounted M6 1A2 Vulcan 20mm rotary cannon, embedded in the right wing root with the muzzle covered by a retractable door. The cannon's firing path is displayed on the pilot's head-up display. Before the F-22 Raptor enters operational service with the U.S. Air Force in the autumn of 2005, it will undergo thousands of hours of rigorous combat testing. Despite this, critics of the F-22 program argue that the F-15 Eagle, which the Raptor is intended to replace, already possesses the attributes necessary to remain the world's premier air superiority fighter well into the new millennium. This view is dismissed by the U.S. Air Force. In March 2003, supporters of the F-15 were given the opportunity to test whether the Eagle was still the best fighter in the sky. 5 F-15s were pitted against a single Raptor in a head-to-head exercise. Although no missiles were used, the sorties closely resembled actual combat, with no quarter given by either side. It was a kill or be killed scenario. All 5 F-15s were piloted by experienced F-22 pilots. One by one, the Raptor brought them down. In these combat tests against F-15s, the F-22 Raptor decisively proved its critics wrong. In December 2005, the U.S. Air Force announced that the F-22 had achieved initial operational capability. During Exercise Northern Edge in Alaska in June 2006, 12 F-22s engaged in simulated combat exercises, downing 108 adversaries with no losses. Over the course of these exercises, the F-22 achieved 241 kills against 2 losses, neither of which involved an F-22. Due to U.S. federal law aimed at protecting its stealth technology and classified features, the F-22 cannot be exported. Instead, U.S. fighter customers are opting for earlier models like the F-15 Eagle and F-16 Fighting Falcon, or the newer F-35 Lightning II. The F-35 incorporates some technology from the F-22 but is designed to be more affordable, flexible, and exportable. Originally, the U.S. Air Force planned to acquire 750 ATFs. However, by 2009, the program was cut to 187 operational aircraft due to high costs, a lack of air-to-air missions because of the focus on counterinsurgency operations, a ban on exports, and the development of the more affordable and versatile F-35. The last F-22 was delivered in 2012. The F-22 Raptor was conceived amid Cold War fears that Russian-made fighters might outclass the F-15. Yet, as the world has evolved since the Cold War, the United States Air Force remains the sole operator of the F-22 as of August 2022. It has 183 aircraft in its inventory. In today's changing world, there are few certainties, but the F-22's dominance over the skies remains one of them. The F-35 was the product of the Joint Strike Fighter, or JSF, program, which was the merger of various combat aircraft programs from the 1980s and 1990s. The Lockheed F-35 Lightning II, unofficially nicknamed the Panther, is a fifth-generation strike fighter development of the United States that incorporates new and learned stealth technology and practices with advanced computer processing and systems through a modular approach. The primary objective of the project was to create a versatile aircraft capable of meeting the needs of multiple branches within the U.S. Department of Defense, including the United States Air Force, the United States Navy, and the United States Marine Corps. To achieve this goal, the F-35 program developed 3 interconnected but distinct airframes, all based on a single-engine, single-seat design. Although there are variations between the production models, all versions of the aircraft retain the supersonic capabilities and possess unparalleled strike capabilities, making them unmatched by any other modern battlefield platform. The F-35 program evolved to become an international effort beyond the commitments of the United States and the United Kingdom, and have included Australia, Canada, Denmark, Italy, Netherlands, Norway, and Turkey to varying degrees. Each nation is expecting to operate the F-35 platform in number at some point, and each player is rated by partner levels in the development. The Joint Strike Fighter program was started on November 16, 1996, as a U.S. attempt to develop a next-generation combat airframe capable of replacing a variety of dedicated fighter and fighter-bomber types then in the U.S. war-making inventory. The new design would have to succeed such proven performers as the Lockheed F-16 Fighting Falcon, the Fairchild Republic A-10 Warhog, the carrier-based Boeing FA-18 Hornet, and the McDonnell Douglas AV-AB Harrier II. No small task, considering the respective successes found by each aircraft throughout the world for time in aviation history. The F-35 originated from the U.S. Joint Striker Fighter, or JSF, program, and went through a 5-year competition phase known as the X-35 against Boeing's X-32. Although both aircraft met the requirements, Lockheed's submission was chosen over Boeing's because it consistently outperformed the latter and was considered a lesser financial risk in the long term. Boeing's X-32 utilized a more conventional vectored thrust approach, similar to the Harrier, for vertical and takeoff maneuvers. In contrast, a third proposal from a Northrop Grumman McDonnell Douglas team presented an interesting lift-plus-lift cruise methodology akin to the Soviet Yakovlev Yak-38 Forger. Lockheed's approach involved a dedicated lift fan system positioned at the aircraft's center mass, just aft of the cockpit, combined with a rotating rear engine exhaust nozzle to achieve a balanced result. Both propulsion units derived lift power from the single engine, and Lockheed's patented lift fan was considered a more feasible long-term solution. The lift fan concept had distinct advantages over the X-32's thrust vectoring system, as it offered cooling for the downward thrust air, reducing the risk of hot exhaust gases re-entering the engine. Additionally, the space saved by the lift fan drive system allowed for increased internal fuel storage in the proposed X-35A and X-35C conventional fighter versions, thus enhancing their operational ranges. This feature was particularly appealing to the USMC, which prioritized a short-range, quick-react aircraft for their STOVL version, the X-35B. Winning the X-35 contract was a significant achievement for Lockheed, with potential revenues of up to $200 billion through the X-35 program and subsequent F-35 production phases. Pratt & Whitney, the engine manufacturer, secured a $4 billion contract for their primary engine supply and development. Additionally, the British government invested $2 billion into the project with the hope of acquiring their first fifth-generation and first stealth fighter aircraft. The production version of the F-35 aircraft originated from 3 X prototypes, with the first one being the X-35A, manufactured at the Skunk Works facility in Palmdale. The X-35A successfully completed its maiden flight on October 24, 2000, and then underwent extensive trials, including in-flight refueling and supersonic flights at Edwards Air Force Base. After concluding 27 flight tests on November 22, 2000, it was converted into the X-35B STOVL variant prototype. Meanwhile, the X-35C, serving as a backup to the more complex X-35B development, was prepared to accept the lift fan assembly if needed. The first production F-35 Lightning II took its inaugural flight on December 15, 2006, and the first F-35A completed its flight testing at Edwards Air Force Base on October 23, 2008. Soon after, on November 13, 2008, supersonic flight was achieved. The X-35B achieved its first flight on June 24, 2001, demonstrating a complete and sustained hover cycle, conducting 8 vertical takeoff operations and 27 hover landings. The production STOVL F-35B began its flight testing phase in 2008, with the first F-35B taking its first flight on June 11, 2008, and the second F-35B completing its maiden flight on February 25, 2009. The first aerial refueling exercise for the F-35B was successfully accomplished on August 13, 2009. The carrier-capable X-35C made its maiden flight on December 16, 2000, and subsequently underwent a series of rigorous mock carrier landings to assess the modified airframe performance. The X-35C demonstrated excellent low-level, low-speed approaches that the U.S. Navy sought in their new combat aircraft. After completing a total of 73 test flights on March 11, 2001, the production 35C was revealed on July 28, 2009, with its expected first flight scheduled before the end of 2009. The F-35 test program reached a milestone with its 100th flight on June 23, 2009. Initially, the F-35B for the USMC was anticipated to be delivered around 2012, making it the earliest of the 3 variants, while the U.S. Air Force expected deliveries of its F-35A model in 2013. The U.S. Navy's F-35Cs were expected to be delivered in 2015. The projected lifespan of the F-35 airframe extended beyond 2030 and was estimated to continue into the 2040s. The F-35 is equipped with an advanced electro-optical distributed aperture system, or DAS, that provides the pilot with a comprehensive view of the battlefield from all angles of the aircraft. The DAS enables the F-35 to detect and coordinate enemy aircraft, air-to-air and surface-to-air missile launches, and ground explosions. Both the short takeoff and vertical landing, or STOVL, and conventional landing variants feature high levels of automation to streamline operations. The aircraft also offers enhanced pilot vision for day and night sorties. The DAS system was developed by Lockheed Martin Missiles and Fire Control in collaboration with Northrop Grumman Electronic Systems. Additionally, the F-35 is equipped with an all-new electro-optical targeting system, or EOTS, developed by Lockheed Martin and Northrop Grumman. This targeting system provides the pilot with enhanced target detection and tracking capabilities at extended ranges, making the F-35 one of the most lethal combat aircraft in the skies. The EOTS is located on the underside of the nose assembly. Stealth technology advancements learned from the Lockheed F-117 Nighthawk stealth fighter have been extensively incorporated into the F-35 Lightning II design. The engine nozzle is designed to be stealth-friendly and axis-symmetric, reducing the aircraft's radar signature while maintaining a minimal profile. The F-35 avionics suite, produced by Northrop Grumman Space Technology, features data sharing capabilities, allowing the pilot to share real-time information with Allied air and ground forces through a satellite data link system. The communications suite, developed in collaboration with international partners, ensures robust and adaptable communication capabilities. For situational awareness, the F-35 is equipped with an AN/APG-81 series active electronically scanned array, or AESA, radar developed by Northrop Grumman Electronic Systems. This radar system enables the pilot to detect, track, and engage targets on land, water, or in the air over significant distances. The radar can also operate as a passive receiver. To enhance pilot situational awareness further, the Distributed Infrared System, or DIRS, consists of 6 internal sensors strategically placed around the aircraft. These sensors provide a real-time infrared image of the aircraft's surroundings, projected directly into the advanced helmet worn by the pilot, offering a complete 360-degree view. The F-35's engine inlets are designed with diverterless fixtures, reducing weight and complexity by minimizing moving parts. The aircraft features a helmet-mounted display system, or HMDS, developed by Vision Systems International, LLC, which delivers critical mission and system data directly to the pilot's helmet visor. This advanced system eliminates the need for a conventional heads-up display and allows the pilot to track and engage targets without facing them directly. The cockpit is equipped with a large panoramic multifunction display system, providing real-time information and high-resolution imagery. The F-35's cockpit supports direct voice input through a speech recognition system and incorporates a Martin Baker US-16E ejection seat. Flight control is achieved through a conventional hands-on throttle and stick setup. The F-35's onboard systems are highly configurable, allowing adaptability to various mission requirements, whether it's air superiority or ground strike operations. With its cutting-edge technology and unparalleled capabilities, the F-35 Lightning II is a force to be reckoned with in modern aerial warfare. The primary propulsion for the F-35 is provided by a single Pratt & Whitney F-135 afterburning turbofan engine. Initially, a second engine option, the upgraded F-136, was in development under a joint effort by General Electric and Rolls-Royce. However, development of the F-136 was terminated in December 2011. The F-135 engine is an afterburning turbofan, delivering 28,000 pounds of thrust on dry power and up to 43,000 pounds with full afterburner engaged. Positioned in the middle rear portion of the fuselage, the engine allows the F-35 to reach a maximum speed of Mach 1.61 and soar to altitudes exceeding 50,000 feet. The rate of climb and G limits vary based on the variant, with the A model having a 9G limit rating. For the F-35B production model, vertical flight capability is achieved using the Lockheed Martin patented shaft-driven lift fan. This lift fan system, built by Rolls-Royce Corporation of Indiana, consists of the fan itself, a clutch, 2 roll posts, and the drive shaft connecting the lift fan to the power plant. Working together with the 3-bearing swivel module, the thrust vectoring nozzle at the aircraft's tail, the lift fan enables balanced lift during vertical flight. Powered by a 2-stage turbine on the engine, the lift fan can generate up to 20,000 pounds of lift, nearly half of the total vertical flight thrust. Additionally, the lift fan provides cooling for the downdrafting air, which is an improvement over previous short takeoff and vertical landing systems. The airflow through the fan is regulated by variable inlet guide vanes. Standard armament for the F-35A production model is the GAU-22A 4-barrel 25mm cannon with 180 rounds afforded. The F-35B and the F-35C also feature this weapon, though through an external mounting and given 220 rounds. The pod itself sports stealth designing to keep the signature of the F-35 airframe in check. To comply with its stealth requirements, the F-35 typically houses its primary ordnance in internal bomb bays, while 6 optional external underwing pylons provide the bulk of the weapon's payload carrying capability. Because of the F-35's international appeal, the aircraft is capable of fielding some foreign-born weapon systems available in the UK, Israel, and the NATO arsenal. Some analysts have criticized the F-35, claiming it to be overly complex, deficient, and prone to breakdowns. Additionally, they argue that it may not be well suited for the missions it was originally designed for. Over 20 years of R&D, that lightweight replacement fighter got heavier and more expensive as the Air Force and lead contractor, Lockheed Martin, packed it with more and more new technology. Yes, we're talking about the F-35. The 25-ton stealth warplane has become the very problem it was supposed to solve. And now America needs a new fighter to solve the F-35 problem, officials said. With a sticker price of around $100 million per plane, including the engine, the F-35 is expensive. While stealthy and brimming with high-tech sensors, it's also maintenance-intensive, buggy, and unreliable. The F-35 is not a low-cost lightweight fighter, said Dan Ward, a former Air Force program manager and the author of popular business books including The Simplicity Cycle. Brown's comments are a tacit admission that the F-35 has failed. As conceived in the 1990s, the program was supposed to produce thousands of fighters to displace almost all of the existing tactical warplanes in the inventories of the Air Force, Navy, and Marine Corps. The Air Force alone wanted nearly 1,800 F-35s to replace aging F-16s and A-10s and constitute the low end of a low-high fighter mix, with 180 twin-engine F-22s making up the high end. But the Air Force and Lockheed baked failure into the F-35's very concept. They tried to make the F-35s do too much, said Dan Grazier, an analyst with the Project on Government Oversight in Washington, D.C. The complexity added cost. Rising costs imposed delays. Delays gave developers more time to add yet more complexity to the design. Those additions added more cost. Those costs resulted in more delays, and so on and so forth. 15 years after the F-35's first flight, the Air Force has just 250 of the jets. The F-35 has not had a trouble-free path in its fielding, nor has any new combat aircraft. The reality is that each generation of combat aircraft pushed technology to the edge, and this involves distinct challenges and a learning curve. The real question is whether the trends of mission capability, availability, unit, and operational costs are headed in the right direction. In the case of the F-35, this is certainly the case. For the members of Congress slated to attend this week's oversight hearing, it may be worth recalling the advice of Sir Frederick Handley Page, a British aviation pioneer. Nobody has ever won a war by trying to run it on the cheap. Nothing is so expensive as losing a war by saving money. If you want the cheapest possible Air Force today, it is very easy to standardize on a whole lot of aircraft that will be of no use when the war comes. For 80 years, Skunk Works has pushed the innovation envelope, failing fast to prove out novel technologies and deliver disruptive solutions for our customers. Strap in as we take a quick trip through the years to reflect on the critical work Skunk Works has accomplished, all of which informs the work we're doing today and in the future. As we look at the technologies Skunk Works continues to develop now and for the future, it's just as exciting and as classified as Skunk Works' illustrious history. Work continues in critical areas like UAS, hypersonics, artificial intelligence, low observables, and other revolutionary technologies. A prime example that is not being developed under the cloak of secrecy is the team partnering with NASA to develop and build X-59, the prototype that will quiet the supersonic boom. The way we engineer and build these capabilities is evolving too, as we lean more and more into a digital approach that reduces cost and accelerates development. The unique and proven Skunk Works philosophy has enabled the impossible to become reality for 80 years. This dedicated and growing team continues to embrace Kelly Johnson's motto, "Be quick, be quiet, and be on time." We innovate with urgency to push the boundaries, ensuring our customers have the capabilities needed to stay ahead of ready.
We knew that, overflying Russia for 4 years, that they were making important advances in radar and missiles. And so in 1958, 2 years before Gary Powers was shot down, we decided we'd try to make a follow-on airplane, which became finally the SR-71, to fly higher and 4 times as fast. So that's the connection between the grandfather type and the SR-71.
Everyone called him Kelly, and as he reminisced that day about the genesis of his Mach 3 masterpiece, he could have just as easily reflected back on a time when aircraft designers were striving for 200 miles per hour, a time when he landed his first job with the fledgling Lockheed Aircraft Company. In 1932, a small group led by Robert E. Gross had purchased Lockheed out of bankruptcy for $40,000 and staked the company's future on the development of an all-metal, twin-engine transport. Models of the design were sent to the University of Michigan, where a young graduate student named Clarence L. Johnson conducted wind tunnel tests. Although his faculty advisors gave the design a passing grade, he wasn't much impressed, and after he had been hired on as a tool designer at Lockheed in August of 1933, he let Chief Design Engineer Hal Hibbard know about it. Among other things, it'd be directionally unstable, especially with one engine out. A rather presumptuous and certainly unconventional way for a 23-year-old to start his career with a new company, but it was only a hint of what would follow. The son of Swedish immigrants, he'd been nicknamed Kelly by classmates because of his quick temper, stubborn tenacity, and unwillingness to back down from a fight, even against overwhelming odds. Instead of reminding the outspoken young man of his place, Hibbard suggested he go back to the wind tunnel and see if he could improve the design. After 72 test runs, he came up with the solution, an unconventional twin-tail arrangement soon to become a Lockheed trademark. And the Model 10 Electra became the foundation for Lockheed's future growth as various models of the airplane helped revolutionize commercial air transport in the 1930s. With his work on the design, Kelly Johnson became the 6th member of an engineering department in an industry which then couldn't afford specialists. Working often simultaneously as an aerodynamicist, stress analyst, weight, wind tunnel, and flight test engineer, he also put in long hours out in the shop, getting hands-on production experience and learning firsthand the importance of designing producibility into an airplane. It was a real-world education on all phases of design and development that within a decade couldn't be duplicated, and the lessons learned became guideposts for the rest of his career. He flew, for example, as flight test engineer on all models of the Electra, and worked for some of the most notable figures in aviation, such as Amelia Earhart. Out of this experience came his lifelong conviction that the designer had to be able to test his own airplane. As he later commented,
I decided at an early age that unless I had hell scared out of me once a year, I wouldn't have the proper balance to really design new airplanes of any type.
Kelly Johnson would log more than 2,300 hours as a flight test engineer. The versatile Electra spawned 2 major developments. One was the XC-35, a modified Model 10, which in 1937 first demonstrated the practical feasibility of transforming the entire fuselage into a pressurized cabin to permit comfortable high-altitude flight. Johnson was Lockheed's flight test engineer on this project, gaining first-hand experience with the problems of pressurization, and more important, with the tremendous possibilities pioneered by this aircraft. Possibilities to which he and Hall Hibbard began to give serious consideration. Meanwhile, the Model 14 Electra incorporated a number of Johnson innovations, such as the first practical application of Fowler flaps, which both increased the wing's lifting surface and served to permit slower, shorter distance landings, an achievement which won him the 1937 Lawrence Sperry Award. In 1938, the high speed and innovative features of the Model 14 attracted British interest in its potential as an anti-submarine patrol plane. But the requirements necessitated a major redesign. Johnson worked around the clock for 3 days to transform the Model 14 into the Hudson bomber. The British ordered an initial batch of 250 aircraft, at that time the largest production order ever received by an American company. But there would be many more, 2,000 to the RAF alone, out of a total production run of nearly 3,000 airplanes. The Hudson put Lockheed into the big time. But even as production was gearing up, Kelly Johnson and his colleagues were well into other much more ambitious designs. The success of the pressurized XC-35 and the recognition that the next generation of air transports would be much larger, higher-speed, transoceanic aircraft inspired Johnson, Hibbard, and a small design team to lay out the now classic lines of the Model 49 Constellation in 1939. Using his soon-to-be legendary powers of persuasion, he convinced Lockheed to build its own wind tunnel, a decision that paid for itself many times over during the development of this design, as all aerodynamic problems were overcome early on, and not one external change had to be made to the actual aircraft. Hibbard was so impressed by Johnson's wizardry that he swore he could see air. Commercial development of the legendary Connie would be delayed by the war, and it first flew as the Army Air Force's C-69. This, however, provided time to refine the airplane so that at war's end, Lockheed was postured to capture a lion's share of the commercial market, and various models of the elegant Connie would continue to grace the world's airways into the late 1950s. At the time he laid down the basic design of the Constellation, Johnson was already well into another path-breaking project. In early 1937, responding to an Air Corps requirement for a high-altitude interceptor capable of 360 miles per hour, Johnson and Hibbard hastily conceived some possible configurations, depicted here in one of Kelly's rough sketches. As Johnson observed many times, in design, you're forced to develop unusual solutions to unusual problems. Their decision to go with an unconventional twin-boom configuration was dictated by another axiom. Design features are the creatures of necessity. The twin booms evolved as a logical development of engine nacelles which had to be extended to house the liquid-cooled engines, turbo superchargers, radiators, and main landing gear. It seemed logical, then, to simply extend the nacelles into booms which could carry the empennage. Their novel approach produced a winning design, and when the XP-38 was finally rolled out in January of 1939, its sleek lines bespoke speed. And when Lieutenant Ben Kelsey took it up for its maiden flight, it delivered an impressive 403 miles per hour, far exceeding the requirements. Thus began the saga of the P-38 Lightning. The first American aircraft able to fly at such speeds, it offered dazzling performance and a host of new problems. For as it peeled over into dives at high altitudes, it could hit speeds approaching 500 miles per hour. In this region, the aircraft began to violently shake and nose over into increasingly steeper angles, and control forces became so heavy pilots couldn't pull out. Tragically, some never recovered. Kelly Johnson wasn't taken by surprise. Although many insisted it was tail flutter, he immediately recognized it as the then little understood phenomenon of compressibility. At 500 miles per hour, Localized airflow over certain parts of the aircraft was reaching supersonic velocity, and this produced shock waves and serious problems. The P-38 was the first aircraft to encounter this, and so little was actually known about it that Johnson launched exhaustive wind tunnel studies and an accelerated dive test program headed by Chief Test Pilot Milo Burcham. After more than 2 years, he finally identified the problem as shock stall on the wing, which reduced lift and increased drag, thereby inducing the nose-down tuck. Typically, he was quick to devise a cleverly simple remedy: a dive flap mounted to the main wing spar that, when deployed, generated a positive pressure field, immediately restoring lift and a nose-up pitching moment. Flown on every battlefront, the P-38 excelled in combat. Christened the fork-tailed devil by Germans, the versatile fighter, combining speed and load-carrying capability, proved adaptable to a wide array of combat roles, and its long legs made it ideal for the vast reaches of the Pacific, where it destroyed more enemy aircraft than any other Allied fighter. Impressive though it was, Kelly Johnson was never satisfied with it. He'd long foreseen the inherent limitations of prop-driven aircraft, and though unaware of developments in Germany and England, where turbojets had already been successfully developed, he decided that props had to go. Thus he and Hibbard became the first in this country to seriously pursue the possibilities of turbojet propulsion, when in 1939 they asked Nathan Price to design an experimental turbojet power plant. Design of the L-1000 got underway in 1940, and by 1942, Price had come up with a truly advanced design, a high compression ratio, twin spool, axial flow power plant promising an extraordinary 5,100 pounds of thrust. Meanwhile, Johnson and a young engineer named Willis Hawkins led a design team that came up with the L-133, a truly radical twin-engine stainless steel aircraft featuring thin wings and canard surfaces and projected to achieve 625 miles per hour at 50,000 feet. But surprisingly, when Johnson submitted a proposal for development of the engine and airframe in March 1942, the Army Air Forces showed little interest. Although launched long after his effort, top-secret development of an American turbojet fighter powered by a British Whittle engine was by then already underway. The Bell XP-59A first flew at Muroc Army Air Force Base on California's high desert in October of 1942, but it proved to be underpowered, overweight, and scarcely optimized for jet flight, and early on, the Army Air Forces decided that it wouldn't meet frontline fighter requirements, though Bell didn't yet know this, and the testing continued. On June 10, 1943, a Bell engineer at Muroc reported back that Johnson had been permitted to examine the still top-secret XP-59A, and he wondered what he was up to. Unbeknownst to Bell, the Army Air Force had already asked Lockheed to submit a proposal for a simpler, single-engine jet fighter built around a 3,000-pound thrust Halford H-1 engine, which would be capable of frontline service. Johnson took in a lot that day, but he'd already been wrestling with jet propulsion for nearly 3 years, and he already had a suitable design well in hand. When he made his proposal at Wright Field on June 18th, he made the astounding promise that he'd deliver an aircraft within just 180 days. Getting immediate approval, he was cautioned that the utmost secrecy was required. Lockheed was already swamped in terms of manpower, tooling, and facilities with wartime contracts. But this was a blessing in disguise, an opportunity to implement an idea he'd been pestering Robert Gross about for years. Let him round up a small group of talented people, designers, engineers, and shopmen, put them under one roof where they could all work closely together, and give him complete authority over everything from procurement to flight test. With no other options, Gross said, "Go ahead." Stealing people from around the plant, just 28 engineers, including himself, and 105 shopmen, he also built a small facility out of discarded shipping crates, using a circus tent for a roof. On June 19th, he laid down the principles under which the project would operate. In 1.5 pages, now preserved on old photostats, they formed the basis for how he'd try to operate for the next 30 years. He'd be responsible for all decisions. Paperwork and red tape would be cut to the minimum. Each engineer would be designer, shop contact, parts chaser, and mechanic, and each would remain within a stone's throw of the shop at all times. There'd be but one object: to get a good airplane built on time. The daily log indicates that 2 days later, he laid out the horizontal structure of the organization. No pyramidal, multi-tiered layers of management. Each project engineer and the shop foreman would report directly to him, and in fact, he'd be looking over everyone's shoulder. He wanted information direct from the men doing the work, and if they had questions, they'd get decisions immediately on the spot. He'd promised the airplane in 180 days. As would become his custom, he gave his men 150. The clock started ticking on June 23rd. Forcefully reminded that simplicity is the keynote of good design, the designers jumped into their work. But this was a new kind of operation, and instead of moving from stage to stage, the schedule demanded an extraordinary degree of concurrency. With finished detailed design still many weeks away, the mock-up was started on June 30th and completed by July 17th. By then, milling and fabrication of parts and the construction of jigs to assemble the prototype was already well underway, and by July 31st, the bulkheads were going into the jigs. And section by section, the airframe started coming together. Throughout this period, however, the design process continued. As concurrent wind tunnel tests revealed problems, the wing and the engine air inlets were the biggest headaches. He'd gambled on the wing, a laminar flow airfoil that had never before been tested on an airplane, and of course, nobody had had any experience with inlets. Johnson was willing to accept mistakes on such an accelerated and risky venture, as long as they were reported promptly. Typically, he never asked why, but what are you going to do to fix it? The project was so secret that his group didn't even have a name. The whole setup reminded one of his design engineers, Irv Culver, of the mysterious place where Hairless Joe, one of Al Cap's cartoon characters in Little Abner, ground up skunks, old shoes, and other unsavory ingredients to brew a potent concoction called Kickapoo Joy Juice. So inspired, he answered the phone one day, Skunk Works, Inside Man Culver. Though Johnson wasn't amused, his organization suddenly had a name that stuck. Remarkably, the completed aircraft arrived at Muroc on November 14th, just 143 days after startup. But when the engine was run up 3 days later, there was a terrific roar as the inlet ducts collapsed, sending debris into the engine and cracking the impeller. It took 6 weeks to get a new engine, but on January 3rd, 1944, Milo Burcham successfully completed the taxi tests. And 5 days later, in the chill of the morning on January 8th, Johnson, in white coveralls, overcoat, and stocking cap, worked intently with his crew preparing for the first flight, as over 100 Skunk Works employees stood atop a hill looking on. He wanted everyone who'd worked on the airplane they now call Lulu Bell to be on hand. He told Burcham, "Just fly her, Milo. Find out if she's a lady or a witch." At 9:15, he took off. But only 5 minutes later was taxiing back to report that the landing gear hadn't retracted and that the boosted ailerons felt too sensitive. While the gear problem was being fixed, Johnson assured him that the control sensitivity was normal, and at 10 o'clock he took off again, and this time put on a dazzling 20-minute display, attaining a top speed of 490 miles per hour and reporting a roll rate of 360 degrees per second. Back on the ground, he was able to report that Lulubelle was indeed a lady. The XP-80 ultimately became the first American aircraft to exceed 500 miles per hour. But this was only the beginning. For months, Johnson had been working on a larger, more advanced version with a 4,000-pound thrust General Electric I-40 engine, promising much greater speed. He promised the XP-80A in just 150 days and delivered it in 132. But as Tony LaVere taxied in after the first flight on June 10th, he'd had a few surprises. Center of gravity miscalculations had caused porpoising. A faulty pressurization valve had channeled 325-degree engine bleed air into the cockpit, and malfunctioning flaps had put the airplane into violent rolls. Only his superb flying skills allowed him to bring it back, and Johnson was so grateful he doubled LaVere's bonus, a gesture pointing up the special relationship between them, and indeed between Kelly Johnson and all of his test pilots. Unlike so many of his peers, Johnson both understood and appreciated what his pilots did. He flew with them whenever possible, shared their concerns, always listened, and then acted on their recommendations. The XP-80A's problems were quickly remedied, and it went on to become the prototype for America's first operational jet fighter. Though it wouldn't enter combat in World War II, the P-80 Shooting Star would deliver awesome performance. In January of 1946, for example, Colonel William Council completed the first non-stop transcontinental jet flight covering 2,450 miles in a record 4 hours and 13 minutes at an average speed of 580 miles per hour. In June of 1947, flying a specially modified P-80R, Colonel Albert Boyd completed 4 runs over a speed course at Muroc, averaging 623 miles per hour, and reclaiming the world speed record for the United States for the first time in 24 years. And over Korea in November of 1950, a Shooting Star would down a MiG-15 in history's first all-jet combat. And amply confirming Johnson's methods and his insistence on simplicity, the P-80 would give birth to a number of progeny. Shrewdly sensing the need for a jet trainer, Johnson gambled $1 million of Lockheed money on the development of an F-80C airframe into a 2-seat configuration, which after its first flight in March of 1948 was transformed into the classic T-33, an airplane affectionately called the T-Bird, which would serve as the standard jet trainer for legions of student pilots around the world for the next 3 decades. In response to an urgent Air Force requirement for an interim all-weather interceptor, the T-33, in turn, served as the basis for 3 different models of the F-94 Starfire, which filled a critical void while newer designs specifically tailored for that role remained under development in the early 1950s. Not done yet, the now vintage design would realize its final incarnation as the T-2V1 Sea Star, an advanced, navalized version of the T-33. All of the iterations of the P-80 design were still yet to come, however, as in 1946 he started design work to meet an Air Force requirement for a new penetration escort fighter. Early on, he explored the possibility of applying new concepts, a delta wing, even in-flight variable wing sweep, and then discarded both, some of the more than 60 concepts he'd examine and reject. When the XF-90 finally rolled out 3 years later, it was the victim of ever-changing and conflicting requirements, from a time to climb of 35,000 feet in 10 minutes to 50,000 in 5, 900-mile range to 1,500, and then back to 600, and finally ground attack capability in a high-speed, high-altitude design. This prompted him to build a brawny airframe, over 30,000 pounds fully loaded, and stressed for over 12 Gs. When Tony LaVere took off on early test flights, he had to use rocket assist because the pair of small 3,000-pound thrust J-34s still lacked afterburning capability. The usual post-flight congratulations and festivities belied the fact that Johnson knew he was facing terrible odds. With the same pair of inadequate engines as their principal rival, the McDonnell XF-88, yet half again as heavy because the 88 hadn't been beefed up for ground attack, Johnson's airplane was bound to suffer performance-wise. It was overweight and underpowered, and even when afterburning was finally added, boosting combined thrust up to more than 8,000 pounds, its top speed in level flight was only 668 miles per hour, slower than existing operational F-86s. It achieved one distinction, however, when in April 1950, Levier pushed over into a steep dive, and it became the first Lockheed airplane to exceed the speed of sound. With performance no better than the XF-90s, the McDonnell entry won the competition, but neither design went into production. The whole ordeal taught Johnson never again to take on a job unless the requirements were both well-defined and firm. Even though a failure, the XF-90 went on to demonstrate that he certainly knew how to build a rugged airframe, as in April 1952, it survived the first of a series of atomic blasts, suffering only 20 hours worth of repair work. Meanwhile, Johnson was completing work on a much more unconventional airplane. Designed to meet a Navy requirement for a vertical takeoff and landing, or VTOL fighter, the XFV-1 was supposed to claw its way straight up by means of huge contra-rotating props driven by a twin turbine power plant, providing more power than the airplane's weight. Engine development lagged, however, and after test pilot Herman Fish Salmon first lifted off from the lake bed at what was now called Edwards Air Force Base in December 1953, the underpowered XFV-1 continued to rely on its makeshift landing gear for all takeoffs and landings. Once aloft, however, Salmon was able to demonstrate that it could make satisfactory transitions from horizontal to vertical flight, and that it could hover in the vertical attitude. But, lacking the promised power, and explaining in his words that it's awful hard to fly an airplane looking over your shoulder, Salmon wasn't eager to attempt vertical liftoffs or touchdowns. Neither was Johnson, who, believing a designer shouldn't be afraid to fly his own airplane, had the integrity to recommend cancellation of the whole project. By that time, however, he already had a much more promising design on the ramp at Edwards. When Tony Levier first saw it, he asked incredulously where the wings were. But those tiny, blade-thin wings and everything else about the XF-104 were actually the product of years of careful thought, effort, and Johnson's determination this time to employ his Skunk Works methods. Back in 1947, he'd modified a P-80 with wingtip-mounted ramjets, and with Fish Salmon at the controls, it became the first piloted aircraft to fly on ramjet power alone. These tests supported a major Skunk Works type of effort to explore a whole new realm. At a time when missile and guidance system technologies were still in their infancy, Johnson's team had to design a pilotless Mach 3 testbed to further explore ramjet technology. The X-7 was the product of their efforts, and its tiny, thin, slightly tapered wings, Johnson's solution to the problems of high Mach flight, was then thoroughly tested on rockets and with scale models. The X-7 first flew in April 1951 and went on to a remarkable career. Launched from a B-29, boosted to high speed by powerful rockets, and then flying on various ramjets under test, it ultimately exceeded Mach 4 and climbed well above 100,000 feet. Thus those small, thin wings were already more than just a theory when Johnson visited the Korean battlefront in 1951. Still smarting from the XF-90, he'd gone there to talk to the ultimate customers, combat pilots, about what they wanted in a fighter. To a man, it was higher speed, more altitude, and less complexity. Intent on giving them just that, he made an unsolicited proposal to build a fighter for which no requirement yet existed. When he promised Mach 2 and 60,000 feet in a simple, lightweight fighter, Colonel Bruce Holloway stepped into the next room and within 2 hours returned with a short 1.5-page list of requirements. This time, with a firm, straightforward requirement, Johnson returned to his favorite Skunk Works mode of operation, and less than a year later, in February of 1954, Tony LaVere lifted the XF-104 from the lake bed for its first flight. Though configured with a much lower thrust engine than the powerful J-79 scheduled for the production model, the XF-104 was still faster than any other fighter in the world. But Johnson had produced more than just a dazzling performer. Fanatical about costs and producibility, while design of the prototypes was still underway, he'd set up a small group of engineers to find the cheapest and most efficient way to produce each part of the production airplane, an innovation which would result in savings of about $12,000 per aircraft and millions for his customers. When the press finally got to see the F-104, they called it the missile with a man in it, and they weren't far off the mark. The first Mach 2 operational aircraft in the world that would go on to shatter every significant record on the books. 91,000 feet and 1,400 miles per hour in May of 1958, making it the first aircraft ever to hold both the world altitude and speed marks simultaneously. 3 time-to-climb records later that year. And in 1959, it became the first airplane taking off on its own power ever to climb above 100,000 feet, as Captain Joe Jordan zoomed up over 103,000 feet. This kind of performance clinched the 1958 Collier Trophy for Johnson. While the Starfighter was capturing headlines with record-breaking performances, another, much more exotic Johnson design was unbeknownst to all but a few, almost daily cruising in level flight at altitudes far beyond any official records. It had been born of the massive arms buildup of the early 50s, when U.S. intelligence agencies urgently needed confirmation of reports of major Soviet advances in intercontinental range bombers and ballistic missiles. The decision to proceed with overflights led to a design competition for a reconnaissance aircraft capable of 70,000 feet. Though Lockheed hadn't been invited to participate, Johnson had caught wind of it and hastily submitted a proposal to build the CL-282, essentially a modified F-104 with a wide-span, high-aspect ratio wing. Though it lost out to the Bell X-16, Kelly Johnson wasn't about to quit. Over the years, he'd gotten to know a lot of people in high places, and he developed consummate lobbying skills. With a revised design and promising an airplane within just 8 months, he got the go-ahead to produce 20 aircraft for $22 million. The project, codenamed Aquatone, was directed by the CIA's Richard Bissell, who found the Skunk Works' streamlined, informal method of getting things done much to his liking. Secrecy limited access to a mere handful of CIA and Air Force personnel, which was fine with Johnson because it freed him from a lot of needless paperwork and interference. The urgency of the project also freed him from what he regarded as the tyranny of technical specifications. His customers simply wanted an airplane that could do the job, and all he had to do was deliver on time. While the article, as it was called, was a relatively conventional design, the extreme altitudes at which it was supposed to operate imposed severe demands. Forced to ruthlessly cut weight, he reduced structural components to the minimum and designed delicate, glider-like wings spanning 80 feet and weighing less than 4 pounds per square foot. The fragile airframe was designed around a special high-altitude version of the J-57 engine, virtually hand-built to extremely high tolerances and originally producing 10,500 pounds of thrust. When the disassembled aircraft was unloaded from a C-124 at a remote desert test site in July of 1955, Johnson had met yet another seemingly impossible deadline. After reassembly, it was rolled out into daylight for the first time and painstakingly prepared for its taxi tests. On August 1st, as he had so many times in the past, Tony LeVere climbed into the cockpit. During his third run that day, he suddenly noticed that he was more than 30 feet off the ground. Coming down hard, the tires blew and the brakes failed and caught fire. Reporting afterwards, he explained that at 70 knots, I became aware of being airborne, which left me with utter amazement, as I had no intentions whatsoever of flying. Those fragile wings had more than enough lift. He completed the first real flight 4 days later, and on a subsequent flight reported that the aircraft climbed toward the heavens like a homesick angel. To conceal its true purpose, the Angel was given the misleading official designation U-2, and a cover story was released to the effect that it was being developed as a high-altitude research vehicle for the National Advisory Committee for Aeronautics. While it would perform this role admirably, tests focused on preparing the U-2 for its real mission, to carry 700 pounds of high-resolution camera equipment up to altitudes then beyond any air defense capabilities. And in July 1956, just 11 months after first flight, it commenced its clandestine operational career. Climbing to well above 70,000 feet as fuel burned off, the U-2 successfully completed flights over denied areas and brought back the first hard data on the status of Soviet military preparedness and the true extent of its intercontinental ballistic missile program. Called the Dragonlady by its pilots because it reminded them of the beautiful, mysterious, and sometimes treacherous character in the Terry and the Pirates cartoon strip, it flew with virtual impunity for 4 years until that day in May of 1960 when Francis Gary Powers was shot down by a surface-to-air missile. While deep penetration of Soviet airspace came to a halt, the U-2 continued to overfly hotspots around the world, such as in 1962, when it confirmed the existence of missile launch sites in Cuba. And it would also continue to perform an incredibly wide array of extremely high-altitude research missions. Kelly Johnson had reason to be proud of his Angel. The Skunk Works had finally been formally established as Lockheed Advanced Development Projects, and on this, its first production program, he'd refunded $2 million from the original $22 million contract and built an additional 5 airplanes out of spare parts. Surely one of the best bargains in defense procurement history. That pride was rekindled when in 1981, the larger, more sophisticated TR-1 was rolled out years after U-2 production had ended. It was the first time the Air Force had ever put an aircraft back into production. And it remains to this day the highest flying single-engine piloted aircraft in the world. Back in December of 1956, the Skunk Works' remarkable performance on the U-2 had convinced Lockheed to give Johnson the job of designing and developing prototypes for a small military jet transport. Dollars were scarce, competition keen, and he'd only have 8 months to do the job. Being on time had always been one of his cardinal rules, and in just 241 days he delivered the Jetstar. He'd actually been working on designs for a large jet transport since 1944. This trim little craft was actually a scaled-down version of the L-193, an innovative 1953 design which the airlines had feared too risky to support. Johnson, who continued to put in long hours as a flight test engineer on this project, was out to prove them wrong. And he was more than pleased with the results. A top speed of over 600 miles per hour, a peak altitude of 52,000 feet, and with wing tanks, a range of over 3,000 miles. The Jetstar easily won the competition, and though only a limited number went into military service as C-140s, ultimately more than 200 were produced, and a great many of them remain in service to this day. The Jetstar was a pleasant diversion as he worked on another, much tougher project. Even as development of the U-2 was still underway, he'd projected that air defenses would catch up with it within 2 years, and he'd initiated a remarkable series of design studies for a liquid hydrogen-fueled supersonic successor capable of climbing above 90,000 feet. Performance varied from Mach 2.5 and a range of 2,200 miles to Mach 4 and 9,000 miles. Because of the extremely low volumetric density of liquid hydrogen, however, the latter speed and range capability could only be achieved by building an airframe twice the size of a B-52. That was far too costly, and thus a much smaller design at the lower end of the performance spectrum went into development as the CL-400 in 1956. Though the CL-400 proved the technical feasibility of a liquid hydrogen-powered aircraft, Johnson was dissatisfied with its short range and convinced that the problems of producing and transporting fuel around the world were insurmountable. Refusing to build an airplane he didn't believe in, he recommended cancellation of the project in 1957. But he had an ace up his sleeve. As concurrent with the liquid hydrogen studies, he'd also examined the potential of another advanced design using jet fuel, which at some loss in altitude promised Mach 3 cruise and 4,000-mile range. It was the genesis of his most spectacular creation. Given approval to proceed, in April of 1958, Johnson began a series of design studies, unveiled publicly here for the first time, for what he initially called the U-3, and then the Archangel, because it would soar much higher than the U-2. He explored various means by which he could get the vehicle to altitudes as high as 150,000 feet, employing a variety, or even a combination of rocket, ramjet, and turbojet power plants. At one point, he looked at the use of balloons to lift it to its rocket boost phase, and then at using a modified U-2 to tow a ramjet vehicle to 60,000 feet for engine ignition. He even considered a multi-staged vehicle, and one with inflatable wings and empennage. And throughout, he was challenged by the urgent need to reduce radar cross-section. For the first time, stealth would have to be designed into the airplane. The intense design gestation process was completed in just 16 months, and when he presented his 12th concept to the CIA and Air Force in August 1959, he got the go-ahead. When the stunningly beautiful A-12 was finally rolled out for its initial tests in April 1962, it wasn't some fantastic, multi-staged aberration. It was an honest airplane, but nothing like it had ever been built before. Ironically codenamed Oxcart and designed for sustained Mach 3.2 cruise at altitudes between 75 and 95,000 feet, it posed by far the greatest challenge of Johnson's career, as everything from structural materials to hydraulic fluid and fuels had to be invented from scratch. For example, because of the intense heat at sustained Mach 3 speeds, averaging more than 550 degrees on the surface of the airplane, Johnson employed a titanium alloy for more than 90% of the airframe. But no one had ever before attempted to process such quantities of the extremely hard metal to the purity and strength levels required. And thus new forging and milling processes had to be invented and perfected. When the thin titanium skin on a wing panel shriveled up during heating tests, Johnson separated the panels from the wing spars with extrusions and put the now famous corrugations in the skin. When heated thereafter, the corrugations merely deepened a few thousandths of an inch and on cooling returned to their original shape, a common-sense solution to a difficult problem. There were literally thousands of such problems to overcome, and as always, Johnson stayed on top of all of them, looking over people's shoulders and asking lots of questions, always the best way, in his view, to get people to solve problems. And he continued to amaze everyone with, for example, on-the-spot predictions of skin temperatures which after hours of calculation they'd find were within 1 or 2 degrees of the exact figure. The whole effort, completed in absolute secrecy with an incredibly small group of people, was all the more remarkable because it was done without the benefit of computers. As Johnson later recalled,
when you think back to 1958, when the basic design work on the prototypes for this airplane was being designed and built, we had to make use of the Michigan computer, which is a 12-inch slide rule, and it did its job quite well.
All of this prodigious effort was about to come to fruition when on April 25, 1962, preparations for high-speed taxi and an initial brief liftoff were completed. But as Lou Schock sped down the runway, he encountered nose-wheel steering problems and had to kick in heavy right rudder. Then, as Johnson wrote in his log, the aircraft got off the ground. There was an immediate change of rudder angle. This set up lateral oscillations which were horrible to see. Schock was lucky to get the airplane back on the ground. The problem was fixed post-haste, and the next day he completed the first unofficial flight with the gear down. On April 30th, Johnson was back with an entourage of VIPs for the official first flight. Looking like he didn't have a care in the world, he offered a few last words of encouragement and advice before Schock taxied out. And from there, everything went flawlessly. "59 minutes later, Schock was back on the ground, welcomed by an elated Kelly Johnson and the small, awestruck assembly who just witnessed something very special. Limited by interim J-75 engines, the A-12 didn't begin to realize its full potential until after the Pratt & Whitney J-58s, for which it was designed, finally arrived in January 1963. At 32,500 pounds of thrust, the J-58 was every bit as exotic as the airplane itself. In combination with an extremely complex inlet and exhaust ejector system, it operated as a normal afterburning turbojet up to speeds of about 1,600 miles per hour, and then shifted to bleed bypass cycle, with the inlet actually providing most of the thrust at Mach 3 cruise. When a two-seat trainer became available in early 1963, Johnson, true to his convictions about flying his own aircraft, jumped into the rear cockpit, and, taking control after climb-out, he'd fly supersonic for the first time in his life. During the course of the test program, a pair of airframes were modified for a highly unconventional mission. In 1964, the Skunk Works built a small, 42-foot-long airframe with the very same materials used on the A-12. Designed to overfly areas deemed too risky for air crews, the D-21 drone would ride piggyback atop an A-12 for Mach 3 launches at 80,000 feet, and powered by a ramjet originally developed during the X-7 program, it would be even faster than the A-12. The finished article was mounted to its mothership, now designated M-12, in December 1964. And on December 22nd, the unusual pair taxied for the first time, and flight tests got underway. After takeoff on launch missions, the M-12 climbed to a rendezvous with a KC-135 for refueling, and then proceeded on to the predetermined launch point, where the backseater would monitor the systems and initiate the launch procedures. While there were several successful tests, it was always a very risky business at best, and Kelly Johnson personally canceled this program after a fatal mid-air collision in 1966. By then, however, he already had two other very successful Oxcart progeny off the ground. The first was the YF-12A, prototype for a proposed high-speed interceptor. It was this aircraft which went on public display when in 1964 President Lyndon Johnson announced the existence of the A-11. And it subsequently put on a dazzling show, as in May 1965 it claimed no less than 9 world records, including a top speed of more than 2,000 miles per hour and a sustained altitude of over 80,000 feet without in any way taxing its full potential. The YF-12 was equipped with an advanced ASG-18 Doppler radar system and configured to carry 3 AIM-47 missiles internally. Though missiles had never before been launched within the YF-12 speed and altitude regime, the aircraft and its systems scored a reported 90% kill rate, even against drones flying head-on down on the deck at distances of 120 miles and more. The Air Force was impressed enough to order 93 of the big fighters into production for the Air Defense Command, but budgetary constraints ultimately resulted in their cancellation. And shortly thereafter, the A-12 was also removed from service, leaving only the Air Force's SR-71, which took over its reconnaissance mission. Though everything about it and its activities would remain cloaked in a heavy shroud of secrecy, this was the aircraft that everyone came to know as the Blackbird. The solid coat of black paint, which seemed to add to its allure and mystery, actually had a very practical purpose. It reduced skin temperatures by about 75 degrees. Its clean, elegant lines and the smooth contours of its blended wing-body shape give the impression that an artist had sculpted it into a rare work of art. In aircraft design, however, more than any other field, form follows function, and here again, every line, every detail of the airplane exists only to serve some practical purpose. The chines, for example, which extend from the wing to the nose and flow gracefully up into the fuselage, actually satisfied a number of requirements. Aerodynamically, they reduced drag and added lift while also enhancing the stability of the aircraft. The SR-71's mission was long-range reconnaissance, and its fuselage was essentially a big fuel tank, and thus the chines also served to house its sophisticated cameras and sensors. Finally, those sloping contours extending up from the chines enhanced the airplane's survivability by reducing its radar cross-section. Thus, while an artist might envy its striking beauty, an engineer would only marvel at the logical genius of its design. That genius was recognized when, in 1964, Kelly Johnson became the first person ever to be awarded a second Collier Trophy. The SR-71 went on to claim the world absolute speed and altitude records, and then repeatedly extended them. And to the public, it always remained Kelly Johnson's mysterious, record-breaking Blackbird. The crews who flew it, however, had another name for it. Throughout its long operational career, it remained invincible and incredibly effective. And to its crews, it was Habu, dark-skinned pit viper with a deadly bite. And though it was finally retired from Air Force service in 1990, Kelly Johnson's Mach 3 masterpiece is still charting the future, its crews still looking up toward the blue-black void of space, flying exotic research missions for the National Aeronautics and Space Administration. When he retired in 1975, Kelly Johnson had been on the cutting edge of an advance from 200 to more than 2,000 miles per hour. He'd been involved in the design of 44 different airplanes, many of them among the classics of aviation history. And at the time, he was still looking very much into the future. He'd gotten the Skunk Works into a project which would bear fruit in the F-117A, the world's first true stealth aircraft. And he'd left a legacy which would leave its mark on the future. It seems kind of ironic that a lowly creature, known primarily for its odoriferous emanations, had, by the time Kelly retired, become a universal symbol for excellence. What was his secret? Well, he had a remarkable capacity to take a complex problem, reduce it to its simplest components, and then take the most direct and sensible approach to its solution. Always a maverick, he was smart enough and tough enough not to follow the committee rule of conventional wisdom. This gave him remarkable freedom. With that freedom came a tremendous burden of responsibility. Finally, and most important, he understood himself well enough to realize that with a few good people, you can do remarkable things. Kelly Johnson's greatest legacy wasn't just what he did, but the way he did it.